Hey everybody, if you're just hopping on, I'm just going to give them a couple minutes for our remote participants to all hop on. So we're going to get started with our humidification class. Again, apologies for the schedule change. Well, those of you who got the email know what happened. So, hey, we don't make that anymore. It's kind of a problem when it doesn't fit the content of the class. But just so you know the order today, we're gonna have Kirby from Tempmaster. If you're not familiar with this Tempmaster brand, that's a JCI brand. Airflow has been selling rooftop units for the past handful of years, but Tempmaster brand goes up to 150 tons. 150 tons. So we're going to talk about, Kirby's going to talk about your ability to do dehumidification controls with the packaged unit. And then we're going to move to a speaker. We're all going to get to know John Hammond. John is the president, CEO of AirGreen. Those of you who've been associated with airflow for a handful of years may recall that we used to sell a liquid Desiccant dehumidification system. They're no longer, unfortunately. John is bringing it back to the market, which we're excited to hear what he's got cooking. And then we've got Bill and Walter from BryAir to wrap up our class from 11 to 12. So looking forward to, we do a lot of in-house training with these events, so we all get sharper and better with our own set of skills. So nice to have a full room. So have we got Kirby on the call? Kirby, can you let us know that you're there?
I'm here. I just want to say for the presentation, are you guys putting up the presentation and I'm saying next slide, or do I need to pull it up on my end? I just want to make sure I've got the communication right. Okay, you got it. Okay, all right. I was just trying to figure out how this looks and works.
So Kirby was nice enough he's I think you're in Norman, aren't you? Traveling, doing something at the shop?
Yeah, yeah, I'm at the Ducted Systems Academy, and in fact, after I get done with here, I have to immediately go give another presentation. So I'm sorry, but I'll be really, I'm gonna have to be very sharp on my time.
Right. So Kirby, do you think you could do an intro for everybody and then hop on into it?
Absolutely. So my name's Kirby Lee. I'm a regional sales manager for the for our team, and I cover the Southeast. One of the neat things about my background is I actually have 20 years of experience in consulting engineering, and my father was an HVAC contractor in Eastern North Carolina, and growing up as a kid, I was swinging a sheet metal hammer, putting together ductwork. Instead of cruising around the mall like most teenagers did. And then I also got the unexpected opportunity to be an owner's representative for a municipality. So I have a lot of experience in contract law in terms of how to bid jobs and procure jobs publicly, and all of the things that contractors, sellers, everyone faces on a public job. So I know all the ins and outs of all the laws of how all that works, because I was the owner's rep that took those bids and tried to deliver projects on behalf of the owner. So I have a unique background that kind of covers everything. I would say and I actually screwed up the title slide. Sorry, this is about dehumidification, but I apologize that I messed that up. But yeah, so that's kind of my background. Is I have a lot of experience in the real world. I cover the Southeast region of our territory for Johnson Controls, and I'm looking forward to sharing with my knowledge. And I'll be very transparent. I am not a traditional applications engineer. So like, if you want to get all up in the weeds of super technical details of something, I will do my best, but I may not be able to give you your answers. But I jokingly tell people that there's this attorney commercial that says, I'm not licensed in Missouri and Illinois, but that's okay. Our attorneys in your state are. So any questions that I can't answer, I am sure Corey and our team we will be glad to follow up on them and see what we can do to help you. So going ahead and put us into mode. So so you can go ahead and are you going to hit next slide or do I need to hit? Okay. So go ahead and hit we appreciate all the partners from Airflow inviting me to speak about this topic. It's been our goal today is to talk about options for dehumidification. There's lots of different strategies about how to do it. And I really highlighted 3 ways because the 4th way is one that I don't have any experience with, and that's going to like a third-party mod shop like Phison. That's my focus will really be on mostly the first 3. So let's go next slide. So today our focus is go back. So our focus today is I want to cover 3 topics. I want to cover 3 ways that I know that are usually successful strategies to do dehumidification. You've got the option for hot gas reheat. We want to discuss how that does dehumidification. We're going to talk about hot gas bypass, which is a kind of an indirect way of doing dehumidification. And then you've got raw valve, which is, we'll call it a tricked out version of doing capacity and dehumidification control. And then at the end of this, we kind of want to recap and discuss strategies that we think that you can take out of this that we think will lead you to success. Next slide. So first topic of the day, hot gas reheat. Go ahead, hit next slide. And then, so the reason why I just brought up the basic refrigeration cycle is to kind of just show, which of course I know I'm not sure the depth of the people in the audience. We may have a lot of experienced people or a lot of people that aren't, but I try to kind of keep things in very common sense, country boy kind of terms of just how things work. And so, basically the idea of refrigeration is essentially transferring energy from refrigerant to the air and then retransferring it in a different form from the air blown out across a fan out into your space. And so what you see happening in a traditional refrigeration cycle is you've got, low pressure liquids, you've got low pressure gas as you go through your evaporator. You become a high pressure gas after it's compressed. And then when the condensing process happens, that transforms into a liquid, which, heat transfer is happening during these processes at the evaporator and the condenser. And then you got an expansion valve, which allows your high pressure liquid to turn into a low pressure liquid. So that's kind of the basics of just the refrigeration cycle. And then if you run into the next slide, you're going to kind of see like a little different version of that. So now what you've got is that you've got hot gas that is high temperature and is high pressure, which is coming off your compressor. You're discharging that gas to reheat the air, and that's leaving the evaporator coil, because when you're coming off the coil, you're at saturation. So no, and obviously cooling and dehumidifying, if you look at the psychrometric chart, is indirectly a process of dehumidification. But reheating the air with the hot gas that comes off the compressor, kind of what we call makes neutral air, and so because essentially it dries the air even lower than it was previously. And so in order to achieve that, you can't just teleport the hot gas, from the compressor over to your coil. And so that's the reason why there's a separate coil there in place. And that's why I kind of wanted to use this basic picture to highlight that, when you have hot gas reheat, you have 2 coils. It's not just one coil to do that work. And that, and then hot gas reheat is obviously a temperature-based, indirectly a temperature-based approach, because you're cooling the air and then you're reheating it. And then obviously as part of that, that's where your dehumidification happens. And then, sorry about that. But But that's kind of that's the strategy about how you're trying to get to your space set point. And is this going to be Tom? This is going to be interactive kind of presentation, or do I need to kind of stop for pause for questions? Do I go through sections? How do I need to do this communication?
That's a great question, Kirby. First of all, if you're remote, please use the Q&A. I think chat just goes to panelists. So just put the Q&A, put your question Q&A. Can you hear me? Someone use the chat function. Let me know if the remote audience can hear me.
Okay, absolutely. All right. Well, in any case, if someone, I can't see the chat right now, so if somebody
there's nothing in there right now.
If somebody fires off a chat, just let me know hey, by the way, somebody had a question. So
thanks, okay. John. Then aside from that, I'm just wondering, in this picture, is the hot gas reheat condenser coil a dedicated coil? Yes,
it is a dedicated coil, separated. You see that this picture kind of right here, that orange device. You see the hot gas line coming off this compressor, and yep. so there's a separate coil there in the system. So essentially, you got like in some applications, like let's say like chill water, for example, like you could potentially have 3 coils in it, right? You could have a preheat coil, if you're in the winter, and you've got freezing conditions. You've got your cooling coil, obviously, and then you got your reheat coil. No, unless you got like a VAV system. And now a VAV system is I would just highlight that this could be slightly different, because you could have reheat at the boxes, and that there are some people that maybe think about different little applications of reheat when you've got VAV, because then the thought is, well, I got heat at the boxes. Why do I need hot gas reheat and heat at the boxes, right? If I'm going to have heat at the boxes anyway, then maybe do I really need or don't need hot gas reheat? So something to think about. I see that there are some questions, or is that chat is disabled? Yes, we can hear you now. Okay, never mind. I'm sorry. Any thoughts or questions about just kind of this basic diagram? I'm a really basic person, so I try to keep things as simple as possible for like the typical average human to understand, and I hope this is a good communication.
Yeah, I've got one more for you. So okay. Is it also a dedicated compressor?
No, because you're pulling hot gas off the hot gas off of the compressor and utilizing it as your reheat mechanism. Now, I would say one of the things that I'm going to highlight about this is that, which I think if you hit the next slide, I kind of mentioned this specifically. So going ahead and hit that part. Okay, so this is actually a little bit kind of prettier version of what I described. Yeah, so go ahead, you can show that. So this is the example of just kind of that pretty diagram, just to show you that reheat coil and what happens and takes place. You got the hot gas coming off the compressor. You got a reheat valve there, so that based on the circumstances that are going on within the system about whether reheat's needed. And then obviously there, for a package unit, there's internal controls where it's trying to, look at all the temperatures that's going on within the system to figure out, does it need to be running reheating, cooling, or traditional heating mode. And then there's a check valve obviously there to keep, to keep any re-entrainment back in the system. So, and then obviously on your condenser side, you don't want anything going back into that back side of the system as well, because that could create some issues. So, so that's just kind of a basic, I call it the prettier diagram of how that works. Go ahead and hit the next slide.
Kirby, 1 second, please.
Yes.
Question regarding what kind of differential we're looking for with the reheat coil, and how is it technically sized? So we have, a discharge temperature coming off of the evaporator coil, and what is like the optimum delta T that we're looking to increase for optimizing dehumidification? Is that something that's a variable in the way this is designed, or is this kind of a, one size fits all solution?
I would for smaller package units, there are different styles of reheat. They have on off, so it's basically one size coil. I would say that generally speaking, for smaller package units, I mean, you see air coming in reheat mode usually off of 70-degree neutral air, kind of, or some type of dry neutral air that comes off of it in some way, shape, or form. And I could be wrong. Like I said, my knowledge is we're getting kind of into the applications realm, which is a little out of my expertise. But I'm just kind of more the real world engineer, be like anybody typical person in the room, what I've seen. Obviously, there's another version of that, what they call modulating hot gas reheat, where obviously, for bigger tonnage units, which I think, offer that opportunity where you can, control how much reheat you're actually getting, and which comes with bigger package units. So, but yeah, so small package units, from what I've seen, I think 15 tons and below, you can't get modulating. I think it's all single stage, on off reheat as we call it. And then I think above 15 is where, you have the option for modulating. Does that answer your question?
Yes.
And Kirby, when you say so one of the systems that we spend a lot of time in is displacement, where we're trying to hold maybe 62 degrees plus or minus a couple degrees. In a modulating system, how manageable is that?
You talking about a 62-degree room?
62-degree discharge air. So you're coming up from
discharge. Oh, so you're talking coming off the coil. Are you talking about leaving the unit in dehumidification in 60 degrees?
After the reheat coil, trying to hold 62, 61, 63, 60, something like that. How manageable is that with the hot gas reheat system?
I think it's possible, but I would be honest, you're kind of going outside of my expertise. I don't have the knowledge, and like I said, I'm very transparent. I'm not an applications engineer, and I don't have the experience to answer that question. So I'm sorry.
Fair. All right. Any other questions on this before we move on? Audience? All right. Take it away, Kirby.
All right, going ahead and hit the next slide. So I like talking about hot gas reheat and all these different dehumidifications about, we'll call it benefits and considerations. And so one of the biggest topics of hot gas reheat is energy code, because there's a lot of energy code out there is a little really tough on people simultaneously heating and cooling at the same time. And that has gotten tougher and tougher as a result of ASHRAE standards and ICC standards or ICC codes and lots of other stuff out there. So that's one of the benefits of hot gas reheat is it's free heat via the reheat coil, right? I mean, you're not paying for that. You're taking the hot gas off the compressor and you're using it for free reheat. So I don't know about you guys, but I kind of like free. Isn't that kind of works?
When you say free, Kirby, it's just you're taking that hot gas. Normally you'd be running that out to the condensing coil and running a fan to get rid of that heat. And now you're just using it sort of like I guess it's like a radiator, but you're using it inside your building instead of using it outside the building.
That is a great analogy of it. And I never really thought about it like that. But yeah, I mean, otherwise that hot gas is going to go out to the condenser and get rejected, right? So, I mean, if it's going to be rejected, you might as well use it, right? So this is a strategy that does allow you to do active dehumidification and some temperature control. It's not obviously perfect, like a traditional chill water option. I'm sorry. But that's the thought behind that. And then I just noted here that for smaller units, you usually have on-off option. And that, if you get into larger tonnage units, you will have you're going to have, a traditional modulating option, which, some people really like that. For certain applications, you may, modulating is something that might be important. Now, here is something where I kind of get into some factory kind of stuff related to this. And this is just my experience across multiple manufacturers. There may be somebody out there that can field retrofit this, but I have never seen it. But my understanding is that that the option for hot gas reheat goes away the second it leaves the factory. And if there is some way to do it out in the field, and I'm happy to take feedback from our audience, if someone out here knows of a way that that can be done that I'm not aware of, I know, then you'll be the first. So it's very, so I would say that you need to pay attention to your climate, pay attention to where you are, what part of the country you're in, what the application is, and then make sure that make sure that you that you don't you can't come back and say, hey, just kidding, oh, I meant I wanted to get reheat on this, and it's like, well, it's too late, it left. And then something else to consider is that from an engineering standpoint, I have not seen, and I know our applications team actually pointed this out to me the other day, was a heat pump option is not available to have hot gas reheat on it. Now, what I have seen is there are some people that will trick the heat pump basically into running the cooling and the heating simultaneously, unofficially. And by the way, technically you're not supposed to do that because it doesn't meet code in some cases. But I will say, like in a residential application, I have seen where there is apparently an option where a manufacturer allowed you to disable that lock on the board, so that, because in North Carolina, the energy code specifically says you can't, the thermostat has to lock it out so that when you're in one mode, you can't go to the other and run both simultaneously. So this kind of tricks out that stuff. And then obviously, in the southern part of the United States where I'm at, out in North Carolina, which ironically I'm in Norman, Oklahoma today, but I'm from the Raleigh, North Carolina area, it gets hot. It gets hot as freaking Hades out there. So, and very humid. So, hot gas. If you ever see a unit in the Southeast that doesn't have hot gas reheat on it, I can tell you it's probably an error. What questions do we have about hot gas reheat? I hope I have answered everything. And like I said, I am not a super PhD expert on all this.
Sure. So when you're going into a modulating hot gas reheat, can you talk a little bit about the components that, can you expound upon what's the difference between that and a stage? Is just, do you have a modulating valve instead of a stage valve?
I believe so. And would kind of make sense to me from a common sense perspective, because I've never really I've never really dug into the super micro details of every sequence of operation for some of our stuff, but yeah, my understanding is that valve is on off in a regular situation. But I can get our applications team to really dig up all in the weeds if you want like a real sequence to see the two side by side and see how it's done. Does that kind of help and at least be enough to be dangerous?
Sure, that's just fine.
All right. Any other questions about hot gas reheat? Even though somebody making some comment about that other place in Cary, which ironically, I would hilariously say that I live in the Apex, North Carolina, and I lived in Cary for 22 years before I moved to the other side of the border. So Cary and Apex, I have lived around my entire life. All right. So shall we move to the next thing?
Sure, that sounds good.
I'll jokingly say, in the words of Bill Belichick, we're on to Cincinnati. So hot gas bypass. So a little kind of high level summary is hot gas bypass is a topic, is a means of dehumidification. It is something that, you used to see a lot. But I would say with codes and various things that have taken place over time, it is less likely that you may see it in the future, and that there are some codes that are actually restricting you for even having hot gas bypass. So, so this will be an interesting kind of walkthrough of just how this works, and I want to look at very specific and targeted applications of, how when are the best times where hot gas bypass is successful? because when as somebody that like talks to customers and clients and other people, I always talk about like, I'm not here to say like hot gas reheat is the best thing ever and hot gas bypass is a piece of garbage. You know, it's more to say, here's where hot gas reheat does really well. And here's where hot gas bypass does really well. Because everybody does something really well, right? So let's talk about that. Next slide. So hot gas bypass. So let's give you a super high level diagram of how it works. So you have got, you can see that there's a dedicated line off the discharge side of the off the compressor that's kind of tees off and is runs over into the evaporator. So one of the you have a solenoid valve and a pressure valve that's there that can go that can make sure that the hot gas can run to either your condenser or the evaporator based on your conditions. One of the oh, sorry, I'm all stumbling here for a second here, but the so the idea is that you're introducing hot gas basically and bypassing it around the condenser and sending it straight into the evaporator. And so what happens in this kind of application is, and this terminology is really good because I call it false load. So basically like the evaporator looks like as if it's fully loaded, and you can see, well, hey, if I'm dumping hot gas into it, that's what it is going to kind of think that, right? Because it's going to run really hard, right? When it thinks it needs to. And so this and I actually incorrectly put something on the slide here. It's supposed to, that's top is supposed to keep the HVAC system out of low load conditions. Because like here's a when you're in low load conditions, let's say you have like a church, for example. I'm sure nobody here has ever done like a church job where you got 300 people on a Sunday, right? And then there's I don't know, 0 people the rest of the week, right? So what happens in those applications, right? Do you think the whatever 10 tons that you put in that sanctuary for whatever the 300 person day, how do you think that goes? What happens when nobody's there? Anybody got any questions on that? There's no load. You got no load.
Moisture just builds up in the space and you can't run your compressor.
That's right. So yeah, that's right. So you've got a 10-ton system that you're trying to run when you have a load of maybe 2 tons because maybe your envelope load or whatever else is, anything that's left over in the space when nobody's there, right? Because you don't need any outside air, right? Because there's no people there. You got no people. And so it's just skin load, from the glass and your roof and walls. So what can happen is you could possibly have a coil freeze, you can have a compressor shut down. Your whole system can shut down if you're in a low load situation. And so that's what hot gas bypass is intended to do, is to keep you out of those situations so that you avoid going into a situation that that puts you where you're thinking about, well, maybe this will be my solution to do that. But indirectly, but by running the cooling coil for as long as you possibly can. Remember, when the cooling coil runs, what happens? You're dehumidifying, right? You can't cool and dehumidify. You can't cool and not dehumidify at the same time, right? So that's kind of the tricked out way of indirectly dehumidifying. So hit the next slide. So let's talk about the benefits and considerations of hot gas bypass. So, if you're in a situation like this, you're never going to overcool the space, right? Because of what you're doing. And this also keeps your unit so that it runs better in off-peak load conditions, right? Now, I would say here as a former consulting engineer of 20 years that you would, just because hot gas bypass, yes, is something that you can do to avoid being in a situation like the church job that we just talked about. But another, you also want to hot gas bypass. Think of it kind of like as a Band-Aid, because like in the reality, as a consulting engineer, you should also be paying attention to, well, yeah, 10 tons is what I need whenever all 300 people are in that room. And 2 tons is what happens where, nobody is there. So maybe I need to look at different strategies about how to do that 10-ton load, right? Maybe I do 2 5-ton units. Maybe I do 3 4-ton units. Maybe I do, 4 2.5-ton units. Some combination of differently to stage and do different options to, you can look at different strategies to like split up your unit so that you're not, putting just one single 10-ton unit with one 10-ton compressor, right? Does that kind of make sense?
Yeah, that works.
And then I say this is that's, hot gas bypass, like I said, it's kind of, you see it, or you'll see it around here and there, but a lot of people will look at it and say, well, why do I need to have hot gas bypass? I'll just put a multi-stage compressor on my unit, right? Or a variable speed compressor, right? I mean, wouldn't that kind of do the same thing, right? Because now you can match the load to exactly what you need, right? You'll save energy, you can dehumidify, you can passively dehumidify, right? Because you're cooling all the time, because if your compressor can ramp down to whatever the load is, you never have to worry about any of that stuff. You don't need hot gas bypass if you do that, right? And then something else to consider, this is a factory install option. And I have never seen one that has been retrofitted in the field that I know of. It may be able to be done, but I have never, but that's just not something I'm aware of. And someone can correct me if I'm awful with that. Now, one of the other drawbacks of this is that this is a huge energy consumer, right? Because guess what? If you're running your 10-ton unit, like it's a 10-ton unit all the time, guess what happens when the power bill comes? It's not going to be low. So that's something you want to consider, about that. And then also, I just wanted to note that local codes are getting a lot tougher on hot gas bypass. And then obviously for heat pumps, hot gas bypass is not an option that works with a heat pump.
Kirby, do you still see many people buying hot gas? But is this just a legacy product that hasn't gone away yet?
I would say so. I mean, I would see, like, I've probably seen it for like maybe some bigger tonnage applications here and there. But most people, I think from what I've experienced, have got savvy enough where they're like, well, okay, yeah, I can dehumidify to do that, right? But no, why don't I just split up my units, do a VSD compressor or a multi-stage compressor?
I suppose in the absence of options 10 years ago, this is probably about as good as, maybe not 10, maybe 15.
That's right. Yeah.
As good as you can get.
And I was going to say, and I'd love to have feedback from the audience, but it just seemed like I'd say it was about 10 years ago when hot gas reheat really kind of took off. I mean, and everybody just started putting it in. I could be wrong, but it just, it felt like, it was just kind of like hot gas bypass was what we used to solve all our problems. And then when hot gas reheat came out, I always create funny or interesting analogies because they're easy for me to understand. But anybody in the 80s a big hair bands person? Love hair bands?
All of us.
All of us. So we all had the big hair, right? Well, there was this always analogy that the day that Nirvana's song "Smells Like Teen Spirit" came out, that people jokingly said that was the day hair bands died. And everybody felt like silly that they were wearing big hair anymore when alternative rock came around. And I just remember that as a teenager, like, hair bands were great. And then I was 13 years old and Nirvana came out, and then it was like as if hair bands ceased to exist.
That is an interesting analogy.
So we'll just say that as soon as hot gas reheat came out on the street, it was like as if hot gas bypass went away and everybody felt like forgot that it even existed. And for the most part.
Right. So the takeaway here, I mean, is there an example of when you'd use it?
I'd use a ray wall valve.
I was gonna say, a ray wall valve is sort of a field.
Yeah.
That's
It's a nice, you can retrofit it if you need to,
Yeah.
or
Right.
gives you.
Well, maybe that's a good, Kirby, maybe it's a good time to hop onto that ray wall valve. That's the next.
Well, that's the irony of that is if only there was an option that you could do something that was a little bit better than a hot gas bypass and have some of those benefits. And there's a name for it. It's a ray wall valve. So let's get into that next. And I'm going to be very transparent about the ray wall stuff. I am by no means an expert on ray wall stuff. We have some gentlemen that are very knowledgeable in this area and can do Encyclopedia Britannica of everything you can possibly want to do with a ray wall. So I'm going to try to keep my stuff as high level as possible. And if I don't communicate this in the most flawless and perfect manner, I apologize in advance. So let's walk through the ray wall valve. Going ahead. So what is a ray wall valve? So the idea is that basically it's a pressure control device that allows you to manage situations where you're trying to trick a compressor into managing the load better of instead of just doing hot gas bypass. So you've got a liquid valve, you got your liquid line coming in here. You've got your superheating chamber here that takes place, and then there's a compression ratio valve that's over here, and that's all the components of a raw valve. So go to the next slide. So this is a basic refrigeration circuit, and this is just just to highlight, hey, in the normal world, here's what the refrigeration cycle is. And I know that we kind of walked through this in the very beginning. I'm not going to go through Encyclopedia Britannica of this again, but this is just to highlight this, and then now hit the next slide. So now you've got the traditional refrigeration cycle, and you've got the raw valve, or some people call it raw. I think it's ray wall. I'm not sure which way it is. I'll have to ask next time. But yeah, so what the idea is, it allows you to modulate the system capacity when you have based on lower load conditions. So, when you get a load that drops, your compression ratio valve is, can be adjusted so you can divert whatever capacity into that superheating chamber that's shown in the big blow up picture. So you can dissipate the heat and you can send cool gas back to the compressor, only sending, whatever capacity that you need based on the load to the remainder of the system. So it's a really kind of precise temperature and humidity control, but it's not like all of the stuff we talked about with hot gas bypass, right? But it's not exactly the same as a hot gas reheat coil either, So it's another strategy. You've got if your desuperheating chamber isn't big enough to get rid of that heat, then obviously, and if your compressor superheat gets up some, then your liquid line will start taking. Your liquid system will start taking. Your liquid line will be ejecting from the system, and you'll send cooler gas back into the compressor. And so essentially, what you're doing is you're causing an unload of the compressor, and when you unload the compressor, you're reducing the tonnage of the evaporator, and that obviously lowers your power consumption and helps your compressor out some. So think of it as like an external device that allows you to modulate your compressor. And I hope I haven't really hacked this up. No.
Well, can you maybe do the explanation with the slide of the refrigeration cycle up? So you've got a load that's dropping, and you're articulating something about the compression ratio. Can you start there again?
Actually, in the next slide, if you go in the next slide, I show what that looks like with the raw valve.
Okay.
So you can see, you've got off the
Hey Kirby, can you
yes.
correct? Cassidy's got the mouse. I think
Okay.
all the attendees can see the mouse. Can you see the mouse?
Yes, I can see it.
Okay, why don't you kind of direct traffic so people can follow along, because there's a whole lot of red and blue here. It would be good. I don't want people, I'm finding myself losing my place here. So if you could go
It's fine.
slow. that'd be great.
So essentially, you see that that out, you got the condenser and you got the line coming off the condenser, and that's the liquid line, right? And then I'm sorry, my terminology is all off here. I'm sorry, the liquid, you see you got the liquid line coming out of the condenser after it condenses, right? Out here off the bottom of the coil, right? And then after you come up, because I'm trying to go back in the refrigeration cycle, no, back and forth. Sorry about this. So you go down here and then you turn to the right, and then you go down to the T, right? And then there's a shut off valve for the raw valve, right? So you can shut off and isolate it, right? And then follow it down, follow the liquid line down. And then you see it come right up. And then that's where it comes in. And then this is where your raw valve is. And that's where the liquid line injection comes into the system. And then there is that's the de-superheater that is right here in the middle. So it runs through the de-superheater. And then
What's
obviously
a de-superheater do?
the de-superheater, go back to the previous slide. It's there to dissipate. It's there to dissipate your heat so that you can send cool enough back to send cooler gas back to the compressor. So sorry about that.
Sure.
Like I said, I am not a raw valve expert. I've only used them twice ever. So so from there, no, you've got the discharge. Hold on here. Am I looking at reversed? Now I'm all confused because it says discharge line into the.
It's your hot gas off the compressor.
Yeah, there it is. So yeah, that's right. I think this discharge, the discharge line is the hot gas off the compressor. That's correct.
Okay. So
And
you're
then-
basically mixing the liquid and the gas in that chamber.
That's correct. That is correct. Yeah, that's right.
Okay.
And then from there, you see the suction line off the top. So that you got the suction line off the top so that you can run off the top here. And then obviously there's a shut off valve there because you can service it. And then it mixes there. And then obviously that suction line comes back into the compressor. And then you've obviously got some bulb sensors to kind of see so that the raw valve and the compressor can kind of, so that there can be some feeling out and communication back and forth about how to work together. And I hope I have done that. That's the best I could do with that. Unfortunately, because I'm not a raw valve expert.
Downside to those is that it doesn't tell you what the humidity is in the space at all. It doesn't know. It's just looking at the temperature of the suction line and the liquid line and modulating accordingly. It doesn't know if it's real humid or not, right?
Right.
Yeah, you need a combination humidistat, thermostat in the space, and as long as the unit's running, it'll just operate off pressure. You just need to trick the unit into keep running based
Yeah.
off the fact that it's too humid, and you're good to go because there's no other controls.
And you've put these on a few units, yeah.
Lots of them.
So far, so good.
So you use a thermostat that has a dehumidification setting that then
Yeah.
keeps the call for cooling going.
We'll have a primary temperature and secondary humidity, and then as long as you force the unit to keep running, and like I like to use it, say you got 2 or 3 stages of cooling, you just put the Raywall valve on the first stage, and then you just get all that additional modulation through the system. Or if you can only get a unit that size with 2 stages, all of a sudden now you get 60% more flexibility just putting it on one stage. We have put it on like both stages, but usually just the first stage works really good especially for those cool humid days.
Yeah, but for
That's where
like
they
meeting
really
spaces and stuff, conference rooms, room like this.
Yep.
Where
Yeah, like 70 and raining days kind of stuff. So, but yeah, so lots of really great dialogue and just learning. Thank you for sharing all the information that I heard. So let's go to the next slide.
And you can retrofit.
Yeah.
The one
Yeah, so
units,
that's where I was gonna go.
when
so-
the unit's grossly oversized and they're just constantly overcooling, this is the solution.
So, one of the things, so when you think about the raw valve or Raywall valve, it's a specialized version of hot gas bypass, obviously. So you're using proprietary technology. So that's that's, and you can use this on heat pumps. And then one of the things that I noted, is that our modification center has the option to factory install raw valves on our units. And obviously I don't know what other manufacturers are doing, but, or this can be done in the field. And here is my experience with the two experiences that I've had with, raw valves, is that when, as an engineer, when you typically hear that, you hear, oh bleep, I messed up the load. Somebody's going to sue me. And so, I oversized something. That's usually what happened. And so, so as a former engineer, the very first time I heard a presentation about one of those valves, I was covering my ears and like reliving horror stories of, oh, please, I hope I didn't mess up something. Please don't get nasty emails and lawyers after me. But when I heard, like, when the raw team, walk through like the benefits of using it up front and not using it in a reactive measure, out in the field, which I noted that that's more expensive, by the way. I mean, to cut in one of those things, for what I understand, in the field is very labor intensive and not very fun, and costs a lot of money. Whereas if you do it in a modification center at the factory, in our case, which is what we do, it's controlled environment. It can be done quickly, easily, and it costs a lot less money. And you get all the benefits of like what you guys have described up front. So yes, it does help you mitigate stuff over oversized equipment if that runs. You don't need another line set for a split system. All of this is self-contained within the unit. You're not trying to add another device on a split system, because it's kind of a different animal by itself.
Can you adjust it in the field? Like
Yes, those I think those valves are adjustable out the field. Yes.
Okay.
And then obviously this is better than hot gas bypass, because now you got better temperature and humidity control. But yeah, I mean, this is a way you can dehumidify. I mean, we'll call it a better version than hot gas bypass of a way to do it.
Is it a fair thing to say that it's easy to figure out what to do in the field if you want the compressor to run longer?
I would say so. I mean, I would say so. I mean, based on what I've seen, I mean,
Use Neptronic, they have a combination thermostat, humidistat. Use that. All you need to do is just tell the unit to run. That's it. It's that simple.
Oh, okay. So you're not actually monkeying around with the valve itself.
Once it's set up, it's done. There's no controls.
There's no field adjustment for,
mechanical.
okay.
There's some pressure adjustment that you can set, but basically very well will give you like if it's a 7.5 ton packaged unit, you'll get, and it's single stage, you'll get this much modulation. If it's 2 stage, they actually have a chart that'll tell you exactly what you get.
I got it.
yeah. So, but yeah, this is off a strategy of, I mean, there's actually energy savings benefits when you're thinking about unloading the compressor, with a raw valve. And obviously, I mean, you do get dehumidification, you get that as well. No, not a different version than hot gas reheat, but I mean, but it's a lot better than hot gas bypass. So let's go to the next slide.
I'm assuming you'd sacrifice also some comfort temperature with that, because you have essentially are running the system longer. So it based on the humidity versus the temperature. So you'll satisfy room temperature before you satisfy humidity.
Potentially, yes, that could potentially come up depending on your circumstances.
But again, it's going to modulate down low enough.
That's right.
You're not going to drastically.
So your discharge temperature won't be
No,
as
it'll
cool.
creep down.
Yeah.
Drastic.
All right. So yeah, so let's look through kind of the thing is that you're keeping your compressor on and active, which is good. And that's good for running the compressor is always good. And then when our raw team ran me through some of this, and they said, hey, by the way, the best compressors you know how to not to dehumidify something, not have your compressor run. So when I heard that, I kind of laughed. So that's why I threw this in here. But compressors that are off don't dehumidify, by the way. And that no, the longer that you run your compressor, the more moisture you take out of the system, and that obviously your APR, you're trying to match the capacity based on your heat content. So it's capacity control too, in addition to, humidity control. All right, next slide. So our strategies for success. So we've talked about a lot of different stuff, and let's see how to get you to the finish line. So let's look through hot gas reheat. Just note, hey, by the way, free reheat, that meets the energy code. And just note that you got to watch out for heat pumps, because hot gas reheat and heat pumps don't go together. And then I actually want to note that split systems too. I don't think you can get a hot gas reheat on a split system as well. So that I'm aware of. And these are factory install options only. So hot gas bypass, you can overcool, that prevents your overcooling of the space, but it's being phased out. So you got to pay attention to your local codes. And then you got to watch out for heat pumps as well, because they're not available. And then you got the raw valve, which I noted that we have specialists that do all kinds of, they can geek out all day about raw valves, and doing training sessions for you if you'd like. So I would say one of the things that when the very first time I heard a presentation about raw valves like this depth was, because people say, well, VSD compressor, well, if I do that, why do I need a raw valve? I'm like, okay, well, maybe that's good. VSD compressors have higher amp draws than stage compressors with raw valves on. And, if you're trying to compete, on a job with somebody, maybe if your amps on your compressor in a stage system with a raw valve, they may look better than what your competition is with a VSD compressor. So VSD compressors are great, but there are drawbacks that come with those too. They cost more money, and they're higher, have a higher MCA and MOCP, which is what which is one of the most important things that go out in your drawings as a consulting engineer. So noting that a raw valve is a great option, better than hot gas bypass. You can factory and field install it, and it works on heat pumps if you want. So if you got a heat pump, you're not going to be doing hot gas reheat or bypass.
All right, is that your last slide there, Kirby?
That is it.
All right, well, thanks so much for presenting to us today, and we're going to take a break until 10 o'clock. So thanks a lot, Kirby. We'll see you next time. And
absolutely. Just quick feedback from the group. How was everything? I hope I didn't completely sound like a uneducated crazy person.
Yeah, it was fine. Maybe a little more digging into the details would be great if we do it again, but this is a good overview. So thank you very much.
Okay, you're welcome. I hope you guys have a good day.
Right. Thanks so much. And you can, Cassidy, you can stop recording. All right, guys, we're on a break. We'll see you at 10. Bathrooms across that vestibule, and then there's some downstairs as well. Have some more coffee. If we run out, we'll get you some more.
Stop sharing. So, yes.
All right, everybody, we're back. We're going to get started. So John Hammond, CEO of AirGreen. I met John at the AHR show, and actually I probably was snooping around the internet maybe a year ago, and I was like, oh, this is another liquid desiccant dehumidification company. This is really exciting. It was definitely a passion project for me. So I've been kind of just keeping tabs on John and his company as they're raising money and developing their product and putting some stuff out in the field. So I'm excited to hear what's new with AirGreen, but I'll give it up for John Hammond.
Great, thank you. You're gonna give it to me. All right, so I am John Hammond. AirGreen's mission was to develop and commercialize a reliable and proven liquid desiccant technology. I joined the company
little under 5 years ago. I came in from the outside, having had experience in a number of different startups and brand new to the HVAC world. A little bit of jumping into the deep end of the pool because our founder, who was an elderly British expat who'd worked on this for a couple decades on and off with the EU and over in the States, actually unexpectedly died my 5th week on the job. And he was the one playing around with all the stuff. It wasn't a blessing, but it did send us back into looking at every component that we had built. And given the experience that maybe some in this industry had experienced with Advantix before, which
We're gonna get there.
no problem. Here we go.
That's better.
Some of you in the industry may have had some less than 100% positive experience with Advantix. We took a considerably different approach, which was, let's go slow. Let's make sure everything's right. Let's run it for years 24/7 and make sure that you do what's necessary primarily in a liquid desiccant system, which is keep your brine solution where it's supposed to be and keep it away from everything else. Now, and as a result, and I'll talk a little bit of history, you know, everything that I received when we started has pretty much changed. The materials of construction changed. For example, our casing was a hand laid up insulated fiberglass composite. That doesn't do great in brines, even if it's perfectly made, and our early ones were not. We moved over all of our internals are welded polypropylene. Every connection is spun weld threaded so that everything stays where it needs to be. And then we do a lot of things to make sure that even if we have velocity excursions, that everything's captured. My background is chemical engineering and process control, and composites in a variety of different startups. And I've spent a decade and a half working for DuPont early in my career. I never thought I would have to use all 3 of those things at the same time, but you know, that's what happens. Startups are fun. They certainly are busy, and we're still a small team, but we went through our UL certification testing via Intertech at the start of last year, and we are sending our new models through this year, and then we'll go through some of the other standards as that comes along.
What is the UL test for a unit like this? To throw it in an oven, try to cook it?
Great question. So we don't fit into one of the, you know, normal categories, but a standard UL 1995 testing is one, they look and see if are all your components already rated. So you send them a big bill of materials, they look at those. Everything that's not rated, then they want to test. And you bring it up to their facilities in upstate New York, and they set it up and they run it. They also take it outside with a power washer and make sure electrically everything holds up like it's supposed to be. And if there's any component that hasn't been tested, then they have the abilities to test up to failure. Then once all that's done, you end up having a registered product. So they are trying to break everything.
Yeah.
And you know, cases like, well, I'm buying polypropylene and it's being welded for me. You got to trace that back to the manufacturer and make sure that it meets all the requirements for that specific thing. Now, what's interesting, there's a new standard coming out that is specifically related to HVAC equipment that includes plastic components. And that will be, you know, and you see more and more, you certainly see it in automobiles, you certainly see it in HVAC equipment more and more. They're going to be some specific requirements for testing and validating those components as well.
Okay.
The cynical view is, you know, it's another source of revenue for all the testing agencies. It is what it is. Okay, so air conditioning. It is responsible, this is the super high level value proposition stuff. It's responsible for the equivalent of 2 billion tons of carbon dioxide released annually. Certainly in the third world, air conditioning as the growing middle class, air conditioning in those climates will continue to grow rapidly. And the amount of CO2 produced by air conditioning will offset everything that we've done so far globally. So it's something that needs to be addressed more aggressively in terms of the power usage by air conditioning. And They're expecting another 4 billion of air conditioners to be built by 2050. And that will require a lot of power and that will create a lot of emissions. There was a competition 3 years ago called the Global Cooling Prize. Richard Branson put money in. We participated with an Indian company. They were supposed to fund 10 groups. They ended up funding 7. We were like number 9. But it was a little bit of blessing because we didn't want to fly to Delhi and build equipment. So, but we were in that specific case. They had a baseline energy use for a room type conditioner, more big space conditioner, but not industrial. They wanted to cut energy use by 80%. We had coupled our dehumidification system with evaporative cooling, which you guys know is low energy use. And there are about 4 or 5 months in Delhi where you need to, for that even to work, you have to strip moisture out of the air. We came close, theoretically, to that 80. We're like at 78% on paper, but we didn't get that far. We are designed with sustainability in mind. We can reduce energy by up to 60%. The theoretical limit is 61. We can provide, as you guys are more than well aware, if you manage humidity and temperature, you can provide great comfort and you can have higher temperatures and still be comfortable and save energy. And if we are saving energy, we are reducing greenhouse gas emissions. One of the byproducts of a liquid desiccant system is those strong brine solutions. We'll kill a variety of pathogens. In one of our research programs, we actually did testing with one of our brine solutions against the live COVID virus and had 100% kill rate, diluted all the way down by a factor of 10. We didn't market it that way because that was the same time during COVID where anybody with a blue light was saying they were going to save the world. So you couldn't be heard. But we certainly seen it in some of our indoor growing environment projects where the presence of mold and other pathogens have been taken away. We strive to be competitively priced with current systems. Obviously, that's a broad range of materials. And we have spent the last 5 years with equipment in the field in a variety of applications to prove that it is reliable.
So when you just, and maybe you can answer this one later, but when you say available now, what would be available now? Like how big of a system?
We're building right now our 2,000 and 3,000 CFM units.
Okay.
They have moisture removal ratings of, if we use the dehumidification ratings that people that put in-room dehumidifiers in, like Quest units, they use a residential standard of 80 degrees Fahrenheit, 60% relative humidity. And they give their numbers in terms of pints per day. Our 2,000 CFM units as constructed today will do at those levels about 2,200 pints per day. And the 3,000 CFM unit will do about 3,300. We've just made some changes. We think that number is going to go up a little bit. But like most dehumidification systems, you work with the load that's presented.
Of course.
From a technology readiness level point of view, back in 2018, the first unit was put in at a software training facility, more as a DOAS unit. Their mechanical systems had a hard time in summer keeping up. And we were able to strip the moisture out on the front end and improve comfort there. And that was more about putting a system in and running it continuously, fully instrumented with data historian. We followed that up with another unit that was installed at a garage and an event center. They had certain requirements. That's 100% outside air system that fed two big rooms, 2 standard rooftop units. We treated all the outside air, and then those rooftop units would kick in as needed. They didn't run much in the shoulder seasons. In the summertime, they would kick in August, September on the East Coast. But we were able to save them a ton of energy, and again, running it 24/7. Yeah. Then we did, the Townsend project was an indoor hemp facility in Delaware. They asked us to come and put a system in for them. They were converting over from the highly lucrative practice of processing lima beans to growing hemp indoors for CBD oil. That ran for 2 years in pretty dirty indoor environment. And we learned a lot from doing that as well. But there's no cannabis killed CBD, so there's no money in those markets. And if there is, it's not growing it indoors and powering lights. You can grow it outdoors and make that. And that's that after a couple of years, they shut that down. And then we did our safety testing in late 2022. We commercialized early 22, commercialized then, and now we're in the process of building out a variety of different units. We've added some distributors to our network, and we're right poised to build out our manufacturing now. That's our next phase. Okay, you guys have seen most of this stuff or are familiar with it. You know, it's a big market. This is more of an investor kind of slide. But there's still a lot of upside growth in HVAC. A lot of, replacement of legacy equipment, given new standards and energy efficiency requirements. The market growth is driven by data centers. There's a fair amount of government tax and efficiency incentives out there for electrification. I will not be taking questions about power supply capacity versus electrification, because I don't think we've worked that out yet. And of that, the global dehumidifier market size is about 3.5 billion. It's expected to nearly double by 2030. And then the US market's obviously a piece of that. We believe that innovative clean tech HVAC systems that can sustainably dehumidify and cool are poised to grow in these markets. And that can be wheel guys, that can be guys like us, all of them have a role. Let's see, patents around the world. We've looked at major economies. These are where we sought to get our stuff patented. India, China, Canada, Mexico. The EU is terribly slow, as is India. India's already been approved, but they have to send us the paperwork. And our technology, the patents are basically built around, we generally have our brine or desiccant flow counter to the airflow. We have a multi-stage system, and our desiccant feeds in on the last stage, and it circulates its way through as it reaches first stage. That way, the driest air sees the strongest desiccant, so you can get a little bit more performance when you do it that way. There are obviously liquid desiccant systems out there. Cathamar has one, single stage pack tower with media for their regeneration. Ours is a media-based system. We have basically a fabric that is corrugated. It's like a Munters style media that gets used in evaporative cooling applications. Same sort of setup. It absorbs, 4 to 5% its weight in liquid desiccant. So we present to the airstream a cool surface that is wetted out with a concentrated desiccant solution, which will strip the air and cool it at the same time. So that, and then the regenerator, which, if I made this a full picture, it would look exactly like the air conditioner. So if on the hydronic systems, we're using chilled water to cool the circulating desiccant inside the air conditioner, and we're using hot water on the regenerator. One thing that's different between us and solid desiccant systems is it's very low hot water energy requirements to regenerate. We can do that between 105 and 115. We don't have to go all the way up, to the higher end. So if we're tied to, say, a heat pump, that has
Water to water heat pump can run the whole thing.
Yes. And that, keeps our energy use low. Now, if you have excess hot water energy, then you have to deal with that in some of our applications. We've put a dry cooler in the hot water loop to shed hot water heat so that we can get continuous chilled water flow. We build these where the media comes in pre-fabricated cassettes too. So after 2 to 3 years of service, if that gets fouled and dirty, you can just replace those. And those are not high dollar items. On the liquid side, we have liquid side filtration as the desiccant in the air conditioner. As it absorbs moisture, obviously it becomes dilute. And eventually, it needs to be regenerated in order to become strong again to be effective. That's where the weak desiccant goes over the regenerator. So there's a closed loop of desiccant between the regenerator and the air conditioner. And we're using hot water heater to strengthen that. That's usually done with scavenger air or outside air. So for like an indoor grow facility, where they put all the units outside adjacent to each individual grow room, the regenerator sits outside and it just circulates. It just circulates the outside air through it. It regenerates. One of the things I didn't realize is one of the projects we're actually being compared directly, and that's the subject of the ASHRAE paper here, compared directly with the performance of another vendor's solid desiccant system. It's all energy metered. It's an Exotech system, if you're familiar with them. You know, the fact that from an air side, we're not pushing any indoor air through our regenerator, there's no odor. We're just sending outside air through that regenerator, and it accepts the moisture that we've absorbed from the grow room and puts it right back into the atmosphere. And then in winter months, we have a preheating coil so that the air is preheated to 45, 50 degrees to make sure it's not so cold that we don't regenerate effectively.
Is the hot water, chilled water system the only manner of regenerating, or have you thought anything else?
No, we've been playing around with the refrigerant system today, and we're in a prototype building right now. So and I'll talk a little bit about it later, but the cooler you make the desiccant solution, the more effective it is. So we've gone from heat pump system to CHP or cogeneration system, which some of the cannabis guys do. And they, the chilled water temperatures there are about 42 for us, 41, 42. We get even more performance there. You start to get into the refrigeration systems, and we've gone as low as conditioned air temperatures at 15 degrees and 2 grains of moisture. One pass directly from outside air. So that's very interesting to our refrigeration partner. And as it reduces the number of steps required for makeup air systems and cold storage applications where you have to have outside air because humans work there.
Is your air in, air out in this, that's just like, you're just moving air across the wetted medium, that's not your air path into the building?
Correct.
Your 4 discharge ducts, that's the air going into the building?
4 discharge ducts.
4 exits.
Those are heat exchangers, my friend.
Okay, all right. Okay.
Yeah, I could probably use a label on that. Yeah, so that's just air in and air out. They would be ducts working back there. We typically put sensors going in and out. One of the interesting things from a multi-stage point of view is there are a number of knobs that we can turn. If we're tied to a heat pump, then we can change the chilled water temperature within a range. We can turn individual stages on and off. We can change fan speeds, and all those things go to the performance. One of the things that we learned from operating a single system in the small hemp operation was that we probably should have had a separate chilled water coil, because we really weren't separating latent and sensible very well. And early in the grow, it's all sensible, and late in the grow, it's like all latent. And so there are different criteria for managing those different stages. The plants are helping cool the room late. And so you are humidity dominant. Early on, it's all you're just fighting the lights. And we had to do some interesting things with changing chilled water temperatures to get within the range, but ultimately you had to make a choice to be managed temperature or humidity. If it gets too humid in the room, the plants their growth slows. Get too hot, they die. So, we had to select temperature first late in the grow versus humidity. And since then, we've had separate chilled water coils, in some cases, in larger applications, a separate chilled water air handler in parallel, so that we can send our chilled water to where it needs to be to completely separate, the temperature control and humidity control.
So your basic design, you've got a wetted media, you've got heat exchange, and you don't really care where your sources are coming from as long as they're, what the cooling sources, the heating source, the regenerator and the air conditioner source is.
Right.
That's nice. It just makes it fit more applications.
And this was a little more complicated because this is actually a photo from our pilot plant. So this particular conditioning unit or dehumidifier has a double set of pipes, because we can take either a chilled water source in, or we can take refrigerated desiccant in.
Okay.
So you'll see out of the exit side of the pump, you'll see, 2 legs there, and you'll see 2 feed and return lines. But we do some neat things here. One of the problems with Advantix is they didn't have visibility into their units. Okay.
Until you cut it up, until you cut it open.
Box, right? So we have a little polypropylene box that's tied in to our sumps, okay, and an ultrasonic level. So we have continuous level measurement. Okay. Early on, if you don't know, say you're running a liquid desiccant system and the level starts dropping, right? Are you over concentrating or are you leaking? Don't know. We have fixed dimensions in here. We have we are measuring the liquid level ultrasonically, so we know where that level is, so we know what the volume is. And we have a pressure transducer here. Now we know what the liquid head is. So you do a little bit of simple math, and now you know what your concentration is. So you have continuous concentration measurement. So you can see what's going on at any time. And now we've got a knob we can turn where we can change the concentration of the desiccant in a particular situation. And everything else is instrumented. Like I mentioned before, 2000 CFM unit. Earlier designs were velocity limited. You do not want to create carryover. You don't want to carry your salt solution downstream into ductwork and your customers' stuff. So we were managing managing our velocities and pretty low. We've since done some things different that actually allow us to move those velocities even higher. So this 2000 CFM unit is likely to become a 2500, and its moisture removing capacity on that same residential scale will also go up as well. With the added performance that we've achieved, the units for the same work can become smaller and less expensive.
So that on the regen side, you're heating up in order to remove the moisture from the desiccant,
Correct.
evaporate it essentially.
Yeah.
How is it discharged?
It's going into the discharge air. Most of the time, there are cases where it's on, if we 100% outdoor air system, we usually tie it in with an air-to-air heat exchanger. And that just all the exhaust air out of the building, that moisture will go into that exhaust air. For a growing facility, that's usually completely separate and it's all outside to begin with. So if you're running indoor agriculture in the desert somewhere, right? We wouldn't make sense because you're trying to recover your water because they don't have enough water for you to do what you need to do. And therefore your condensing units are the best choice, provided that you're not capturing other things that you don't want to be in the water. And certainly at the cannabis facility in Pennsylvania, they've got plenty of water. That's not their issue. They have concerns about what if something goes wrong and we get glycol into our recovered water systems. How do we deal with that? I'm not going to get too techie in this. The basic principles are, if you're going to condense moisture out of the air, you got to go below the dew point and then reheat. Those differences in enthalpy for the green line, which is, what we do. There is an exotherm, but it's quenched immediately because we're circulating chilled desiccant. It's a straight path to the final point. And you can draw lots of different curves with solid desiccant systems. And I'm sure you guys will probably talk about that a little bit, whether you're pre-cooling and post-cooling. I'm not an expert in that. I know that the one that we're doing work alongside in Pennsylvania has both pre-cooling and post-cooling. And I know that for the amount of work, with a little bit of apples and oranges here, we were doing that same level of work, same number of plants, same square footage, as very similar light wattages. We were doing that work in about 8 to 10 tons. The capacity of the X-Tech units were compared with for that same work, just pre-cooling and post-cooling, not even including regeneration of the wheel, was 56 tons. In the paper that we have here, this is our system for this cannabis facility in Pennsylvania. You know, we have our liquid desiccant air conditioner. Okay, so we're taking return air from the room. We are cooling and dehumidifying. Alongside, we have a chilled water air handler so that if the air is at the proper humidity conditions, that will divert the chilled water over to the air handler. And the air handler is they have circulation air requirements, so that's continuously running. We have heat recovery, since the desiccant's going in a loop, it's coming back from the regenerator hot, it's leaving the air conditioner, the dehumidifier cold. Those get transferred into heat recovery heat exchanger just to save the energy that's being required for running those units independently. And we have on the regenerator, which sits outside, in very cold months, we will use hot water from the CHP system there. They've got a 4-pipe system, and we'll use that to preheat the air. We don't have experience running regeneration at 4 degrees. Pretty interesting tying in with CHP for the first time. This was not a Yanmar system. This was a Tenem system. And the guys doing it maybe weren't as expert as were hoped. So the first thing they did when they turned it on, they did it without temperature controls. Top end hot water temperature 180. And they cooked us at 215, I think. And so some of our CPVC pipe, they melted. So they had to have us come back in and repipe some of it. There are a number of learning curves with that. CHP is maybe not let's pick the low bidder regardless of their expertise kind of environment. But we have seen from running the colder temperatures, our performance be even better.
On the discharge side, do you have any concerns about growth? Like mold growth and stuff like
It kills
that?
all the mold.
We haven't seen it. Again, these strong desiccant solutions tend to kill molds.
Okay,
Okay, and we've, mold can be a real issue in indoor growing environments. We've been doing that for years. We haven't seen any problems so far. That doesn't mean our customers tell us everything, but we've asked. If you keep everything in the right range and it doesn't get out of hand, you're managing half of it. And if there is anything that, if you're killing it, it's helpful. What we're being compared to in this particular case, again, this is another vendor's system. They have a pre-cooling coil wheel and a post-cooling coil, and then they are using the hot water system to do the regeneration of the wheel. And the systems work. They're fine. We were looking at it from an energy savings point of view, and that data is starting to trickle in now. Now, both those systems are fully instrumented for power usage. Every single component, whether it's fans or controls, you name it, have energy measuring devices on them. And after several 9-week growing cycles, we'll have a full data set. Had it already if they were a year and a half behind on their original production schedule. We literally delivered our equipment almost 2 years ago.
I think we're all familiar with the lead time challenges of the past handful of years.
Yeah. Well, there's a lot of, I was buying heat exchangers last year and they went to 45 weeks lead time. This is what we have 2 units outside at this grow facility. We have 2 3,000 CFM conditioners, and we have 2 2,000 CFM regenerators. The regenerators are more efficient to run, so they don't need to be as big. Our package units, which I'll show, actually have a built-in side-by-side conditioner and regenerator all in the same box, fans, coils, all that. This was, again, 2 years ago. It was more modular being put together, and then you'll see, the desiccant piping going in a loop. This is coming over from the cogen piping over to the preheater and also the regenerator there. It's actually pretty simple. And I think we have twice the capacity we need. Cannabis. It's an interesting market, not nearly as shiny as it was 2 years ago. The profitability of most cannabis operators don't make money. States give out too many licenses. they get oversupplied. California prices went from $2,400 a pound wholesale to $700. And the average energy cost for a cannabis grower in California is $1,000. So most of the people are making money. And California is unique, as we all know.
But they're happy.
They're also taxing everything to death. And it created a huge black market. New Jersey looks like it's poised to be oversupplied. I think Michigan already is. And so our advice to growers is invest in energy efficiency. That's the only real way to create a sustainable competitive advantage. I mean, if you look here, their energy use, 90% of it, almost 90% is either HVAC or dehumidification and running the lines. So sometimes it lends itself to CHP. That's our point, is if you tie in CHP with a liquid desiccant system, you can cut your costs significantly. And then you've got a competitive advantage over all your peers because the states are going to do what the states are going to do. I don't really know how some of the small growers, unless they have some expertise in building a brand that people want to pay a premium for. I just don't know how well they're going to be able to do in the long run. For this was our study that we presented at the HR meeting. If you look at the max load, and this is a thermodynamic analysis, we look at the max load of an individual flower room, and we've compared that with a variety of different equipment. And with that vendor specific equipment using their data. We're $64 and change a day at maximum load for a 2,100 square foot flower room with about 575 mature plants with a weeknight set point of 70 degrees Fahrenheit, 45% relative humidity. So we're $64 a day. What we're compared to, they're 160. Okay. If you look at the liquid desiccant with more non-CHP equipment, we're about 123. Desiccant wheel with boiler chiller and regular DX systems, they're kind of all in the same ballpark. Okay, the wheels do a way better job in the specifically addressing humidity.
So with your LDAC with CHP, so see the regen side with what's the other side?
I'm sorry, could you say that again, please?
So you've got your hot water from your CHP. For those of you who don't know, CHP is combined heat and power. So it's an engine that produces electricity, and the byproduct is waste heat.
Yes.
So in your liquid desiccant system, the hot water from the CHP is regenerating. Are you using what are you using on the air conditioning side for your water source?
They have a 4-pipe system, and they are using the energy in this case from the CHP system to basically run a chiller.
Oh, okay, all right. So there's you have basically two technologies working together to get you that $64.
Yeah, that particular system, they have an electric chiller, and they are giving us 180 degree hot water, 42 degrees chilled water. In our experience, with our system, we're able to control the humidity, and this is actually the hemp facility. We're able to control the humidity easily within ±3. You're kind of approaching sensor capabilities, precision there. I mean, you can 2%. Even though it does drift, that's better than ±3, but you're not going to do a heck of a lot better than that.
Right.
We saw that definitely at some of the DOAS applications. And then the interesting stuff that we've been working on for the past year is using refrigerants to chill the desiccant and looking at cold storage applications where you need outside air, you need make of air systems. You need to make sure that the dew point is not met. Because if you start to some of those places where you get dew, then all of a sudden they have to call the FDA in, you have cleaning procedures and downtime and all of that. So it's pretty important. And from a safety point of view as well. One of the traditional solutions you see in the pharma world in New Jersey is that they've got 3 or 4 pieces of equipment, wheels and coils and chillers, and to get all the way down here into teens. And we're able to do that once through direct. So we can go from outside air, down into, freezing temperatures with dew points well less than 25. And when we pushed it, we actually took our Desiccant temperatures down to minus 37. And made, 27. We made minus 15 degree air at 2 grades of moisture. So our partners are pretty excited about that.
Yeah.
That's pushing the envelope a little bit on materials, and that's obviously just us testing the system as far as it would go.
Right.
Again, very energy efficient, and from a capital cost point of view, less than half the cost of some of the solutions that are out there. This is an overview of our design for this package system. It has a Frio Verde condensing unit, AirGreen conditioner regenerator, filter stands, all that great stuff. It's all in one package unit. Those prototypes are being built right now.
So Advanix had some restrictions just on how much dehumidification you could accomplish with a single unit. Sometimes they would have us do a 2-pass kind of a thing. Yours is really more based on what the temperatures of the solutions you're using for activation in your.
Yeah, that's our primary knob, but again, all dehumidification systems their capacities are based on the loads that are presented.
Right.
Very dry air, you've only got so many molecules in a cubic foot.
Right.
And you can deal with that. And we try to make sure they have enough turn down to deal with a variety of things. It's all design dependent.
Of course. Are you guys working on tools to, hey, if I plug in my reactivation temperature and my air conditioning fluid temperature and my airflow, and this is the kind of dehumidification I should be able, or do you have to do all the designs? No sales tools yet, it sounds like.
Okay, so right now we've integrated Delta controls into our system.
Okay.
We like them because they're non-proprietary and anybody can use them. We are building an algorithm now where you can put it into energy savings mode and sort of start trimming some things. But early on, everything was, hey, if you need to run, and cycle between units as necessary and turn down a little bit.
No, I mean, like if Logan calls me up and says, hey, I've got an application where I need to go lower than what I think a hot gas reheat system would be, but I don't know that I need a full on wheel Desiccant system, something in between.
Right now, we have an engineer do it. We don't have an online tool.
Okay.
An online calculator per se. It's in the works. We're gonna raise a little bit more money first.
Okay, sounds good.
Yeah, we'd like to have that. And an energy savings calculator too. Hey, if I do this, what can I expect to achieve?
Well, reps will find a way to get into trouble, so it's probably a good idea to think it through.
Yeah. No kidding. So, just another application that we've been engaged with. One of the hospital chains asked us to get involved with a demonstration program with them. Operating rooms have a range of humidities they like to operate. It's cold and it's dry, and they want to, they were actually finally have just written code to bring it into that 40 to 60. It was broader than that before. And we think particularly in southern climates, we think putting us on the front end of existing systems is really smart. They're small, compact, standalone. And from a hydronic system, most of those facilities will have a central plant where they have chilled water and hot water available. There is a huge sustainability movement in hospitals. And right now they do most of this work by brute force. Very low temperature, just hammer it and get the humidity down low, and then lots of reheat.
Mm-hmm.
So they're not, they're just hammering it. And it's not as energy efficient as it could be. If you're in Florida and you're running a hospital, why not have dehumidification, built in for the outside air that you're bringing in, and then you can deal with it in a much more energy efficient way without changing a ton of infrastructure. And I was at a conference a month and a half ago. A lot of the facilities guys are looking at the same thing. Universities, central plants lean into hydronic systems where you can pre-treat.
You don't want to run your chilled water plant all the way down just for your OR. But
Say
that's
again?
you don't want to run your chilled water plant temperature all the way down to 42 so your OR works, but then you have really cold water where you don't necessarily need it everywhere else.
Yeah.
So yeah, I can see where this would be great.
Yeah, and we're effective, we don't have to be 42, we're effective at 55.
No, that's what I mean. Like if your OR, you have a central chilled water plant.
Yes.
And you need 42 degrees to get your OR to run at the humidity that you want, you drive the whole chill water plant,
Yes,
right? So this would be an opportunity to say, all right, well, instead of doing that, we can run our chill water at 45
right,
and supplement our ORs with a desiccant system.
Yeah.
You can also do it with a solid desiccant system as well,
yes,
right? So same kind of thing.
right on. So this joint commission, the other ones, putting some pretty stringent goals in front of hospitals. Now, I would argue that hospitals need to do what they need to do to, keep pathogens from growing in operating rooms. So maybe they're not maybe they shouldn't be the first to do some of this stuff, but it is what it is, and we're hoping to help. Okay, what do we have here? So we've got a couple more. We've got some cold storage projects building, we've got 2 more indoor ag projects in the works. This goes in, we're halfway installed there. So basically a brand new furniture and woodworking facility in Delaware where they take at-risk youths and teach them carpentry skills so that they can become employed later, whether it's construction or anything else. And we got a CARES Act grant during COVID to not only do that project and demonstrate, but also to send our desiccant solutions up to an Army test facility where they do, biological warfare stuff. And they tested our stuff against the live virus. They were going to do a demo, would put live virus and a bunch of equipment, and we chose not to do that second part. Mostly because there didn't seem to be a market and all the noise that was going on about my blue light kills everything. So we didn't spend that money. So we're building, this is what part of the package unit design is going to look like with the refrigeration system. AirGreen side by side, conditioner and regenerator, all one neat package. So it can be either hydronic or it can have an integrated refrigerant system in there. Similar to Advantix, except that we've got more room to work on things, and it's not vertical like theirs, and it's not nearly the velocities that they were dealing with as well. And I had the opportunity to take one of their units and bring it home, but it was just too expensive, and I felt like it wasn't worth, looking at. Again, they created a bit of a negative impression over years on liquid systems. I hopefully convince you that if you do the basic stuff and you keep your desiccant where it's supposed to be and not in the airstream and not on the floor and not on the pan, you can do that by choosing the right materials and doing the engineering right. Then these systems are highly effective. We also have, if anyone's ever interested, and you find your way over near the southern New Jersey border and Delaware, which is a tiny state. We have a full-scale pilot plant, fully instrumented there. So if someone has conditions that they want us to test for, we can do it there. Now, we don't make all of our own air at laboratory level, volumes, but we do a pretty darn good job. So that's where we were able to tie in the refrigerant systems. We've got long runs and instruments, so everything works there. And we also use it to keep our shop cool during the summer, which is nice as well. That's most of us. We've done a lot over the last 4 years with a small team. We commercialized a product for a very small number. Again, our philosophy was, let's get it right. Our industry is too conservative to accept failure. We're not writing software, okay, and throwing it out in the world and having people vet it. We're putting equipment in place. It needs to be managed. It needs to be maintainable. And we need to have good people working on it. And we have a pretty darn good team. And we're looking to expand that at least double before the end of the year. That's it. Questions? Did I go too long?
No, you did great. You did great. I have a bunch, but I'd rather have other people chime in first. Audience, remote audience, any?
Sarah, you said right now you're kind of locked into the 2 unit sizes.
That's what we have, that's what is in inventory right now.
Okay.
We are
Is it
building
scalable for larger CFM or?
It is within a certain range, okay, and I'll explain why. We are circulating Desiccant over a piece of media, right? Imagine if that media were infinitely long. Eventually, the Desiccant would become dilute and warm and would stop working. So we're working on a design round, a stackable design where we're taking 2 2,500 units and making a 5,000. So we'll go a little taller. And we're working on some media designs that will improve capacity in that, but eventually you're talking about it's better to buy 2 units at a lower price than a higher cost bigger unit. Then you have some, if something needs to be fixed, you still have something running. So to me, it's like if I have a fan wall and I've got 4 fans and 1 fan breaks, I still got 3, right? So we've seen, and certainly in the refrigeration side, that the cost of a unit twice our size was 3 times as much. So it's cheaper to, have 2, have some redundancy than it would be to spend more money on a bigger unit. But we're working our way towards a solution for 15,000 CFM.
That's a lot of dehumidification at 15,000 CFM.
It is, and there's a little bit of this sort of, since people are used to dehumidifying with airflow, that they get locked around, well, if I'm gonna dehumidify, I need this much. And actually with a Desiccant system, you don't.
Right.
And that's a little bit of an education that we have to go through saying, give us the load, we can tell you what airflow you need. For the cannabis guys, they want circulating air. So a lot of times we're circulating air with no chilled water in anywhere in the system. That's fine, because they want the circulating air. But I don't think we need to get bigger than 15,000, but some of the large pharma units are used to those numbers. And we'll figure out where the right place to be.
Sure. If so you're in this early stage, what would be, if someone called you up and said, hey, I've got this job, and you said, man, that is a perfect job for us, what would it be? Or what are 2 examples of what it would be?
Perfect job. Well, I've got some opinions, okay? One, something we've been looking for, and we haven't found it yet. ASHRAE and the school districts have all said, we need more fresh air. More fresh air means better learning environments, means all these great attributes, right? And so they want to pump more fresh air into units, into traditional mechanical systems that can't handle it. So for me, I want to have a project where I demonstrate that, hey, you guys can pull more fresh air into your school because I am treating it before it goes in. So all the consequences of moving that air through a system that's not capable of handling that increased load and moisture. And I can demonstrate, and you're only adding a little bit of equipment and we can help. The indoor growing, CHP environments are perfect for us. And some of the cold storage stuff looks really good too. But we like this, we like the modular DOAS stuff because we think it's just logical. Hey, we're going to move more air. Humidity is becoming more and more component of all of these systems, and the solution we're having to design and engineer against, and putting us on the front end to take that off the table. All the traditional, very cost-effective equipment does what it's designed to do. We think that's great.
Super.
Yes, sir.
So with the system, so we don't have to cool it down to the new, is that correct?
Correct.
So it's no saturated air in the system, so do we need to worry about the drain or water the system,
No, we are capturing it all into the Desiccant solution, and then the regenerator is putting it into the exhaust air or outside air streams. So there is no condensation to deal with.
What's the Desiccant you just use?
We keep that close.
Ooh, juicy.
We've used a variety of the different Desiccants. And I get asked that question a lot. When we do something with a customer, we do disclose that. Okay. Because they have to know, they need an MSDS sheet. They, those things are necessary. But what we think we're doing is unique. And we'd like to.
Is the Desiccant readily available?
Yes. So a variety of sources. Now, we played with some of the lower cost ones too, right? Potassium acetate, you can use to put on the highway, to get rid of ice. Man, it was a vinegar plant. Okay, it was so much odor. Oh my goodness. But there are lower cost Desiccant solutions that people are working with. The problem is it's a huge performance trade-off. Really, so, cheap, you get what you pay for sometimes. And we don't like calcium chloride. I narrowed that for you a little bit.
All right, how about a nice hand for John?
I do have some stuff here that you can help yourself too, okay? These are nice for chip clips. Yeah, chip clips, or hanging stuff on your refrigerator because it's got a magnet. But help yourself. Thanks, everyone.
Right, and BryAir will be up at 11, so you guys got about 8 minutes and we'll get started up again. That's good to go.
No.
All right, guys. It's a summer thing. Hey guys, got the last leg of our training class here. We've got Walter Rice from BryAir presenting on solid desiccant. Well, solid desiccant, wheel desiccant, however you will articulate. We have to say we've since we started working with BryAir, we've done a lot of little mini pack systems, which is a nice small part of their business. We've had looks at some of the bigger systems. We're hoping to get into more of those. But so far we've, all of our projects have gone really nicely. A few of the people here have worked with us. So with that, Walter, you ready to go? All right, sounds good.
Thank you, Tom.
Thanks.
Thank Airflow for allowing us to be here today. As Tom said, my name is Walter Rice. I'm with BryAir Incorporated. We do dry desiccants. A little bit about BryAir. We've been in business since 1964, located in Central Ohio, just outside of Columbus, Ohio. I've been with the company since 1995. Been in the engineering department, started out as a mechanical engineer, and did application engineering. And now I'm the director of engineering. I've been in the ran field service for a while. Also did some production management off and on during my time with the company. So a little bit about what we're talking about. Desiccants are materials that can capture the moisture and release it, the molecules. So that's kind of the principle behind humidification. So you kind of seen this slide already. Basically, a liquid desiccant is going to remove moisture and cool down the air. The dry desiccant, which is what we use, basically just look at the desiccant rotor itself. Due to the reactivation, the regeneration, that the air gets heated up and as it removes the moisture. So we have two different sides of our units. We have the process side and what we call the reactivation side. The process side is what drives the air. So you got whether it's outside air, return air, or a mix of outside return air going into our unit. Then it enters the desiccant rotor. As that enters the desiccant rotor, the moisture is absorbed. The desiccant rotor rotates at a very slow speed, around 3 RPH to about 15 revolutions per hour. As it rotates, the desiccant rotor enters our reactivation air, which basically releases the moisture back into the exhaust of the unit. For reactivation, we use electric, steam, LP, natural gas, hot water on projects that doesn't require as much dehumidification, or we use hot water also as a booster heat. Sometimes to save energy, we'll put a hot water heater if they got a boiler readily available to kind of preheat the air to get up to So we use less reactivation. Basically, we use silicate gel. We use the Desiccant rotor. Previously, about 1995 and earlier on, we used the silicate gel beads, which were in a container. And the containers rotated in and out of the process airstream. That technology went aside about mid-90s with impregnated silicate gel Desiccant rotors, the dry type rotors. Rotors are non-flammable, non-toxic.
So you make that wheel by having a flat sheet,
A corrugated sheet.
a corrugated sheet, and then the
It
desiccant
is
is like
impregnated on that substrate.
an autoclave kind of a application or,
Similar to-
okay. It doesn't really come off the wheel ever, does it?
No, the silicate gel.
Okay.
Unless you have some kind of a chemical that eats at it and that's in the atmosphere.
Okay.
Basically what we're doing is we're trading heat for water and water for heat. Again, we're dealing with vapor pressure. This is how we're removing the moisture as the Desiccant rotates. So here again, this is what I talked a little bit about. The process air stream. Again, we're going to take the moist air. It actually gets heated up, but it goes down on the site chart as it gets drier. As you see, the reactivation air, we're taking typically reactivation is outside air. That air then cools down and picks up moisture during the cycle. Typically, you'll use Desiccant and you need to get below a 40 dew point. 70% degree, 40% RH, where your traditional mechanical system just can't get down that far.
Hey, Walter, I know it depends, right? But our first speaker didn't go into a great deal of depth about what you can manage with the DX system and hot gas reheat. Do you have any kind of, keeping in mind, yeah, you can have more outside air and you can have different loads and all that kind of stuff. But if you're doing just like a typical application, where would you say that DX units with hot gas
So we
reheat
tell
stop?
people, if they're above a 45 dew point, they should look at a traditional DX system. Below a 45 dew point, you start looking at Desiccant. One of the key factors when you get into, the reheat cycle of a DX system is, now you're fighting between temperature and humidity. Temperatures, humidity is relative to temperature. So if your temperature fluctuates, humidity is going to fluctuate. So at that point, you start looking at how critical is the process. How tight do I need to maintain temperature and humidity? And do I need to separate the two?
Thank you.
So here we're going to look at several examples of a system and kind of how we approach our systems. So for this example, we're just talking about 1,000 CFM outside air. We want to get down to, our goal was a 70 degree, 20% RH, 22 grain, leaving our unit. So we're going to start with the outside air. You see with the standard traditional DX system, I can get down about 50 degrees, 50 grains. You can kind of see that on the site chart. Now we look at just the Desiccant rotor itself. No cooling at all. Again, same goal to get down to that 70 degree, 20% RH. You can see, as we talked about earlier, I'm picking up temperature across the Desiccant rotor, and I'm dropping off moisture. So I'm able to, with just the Desiccant rotor itself, get down to 70 grain, based on 100% outside air of 1,000 CFM. You see that on that site chart as well. Now, what we'll typically do when we need to get lower grains, we're at pre-cooling. Again, this is to keep the energy costs down. Mechanical cooling is, the lowest cost of cooling, of dehumidification. So we use a pre-cooled coil, typically chilled water or DX. We use both in our systems. So we're taking that same outside air at 116 grains. We're dropping it down to 55 saturated before we enter our Desiccant rotor. And there you're able to see I'm able to get down to 22 grains, which is what I require on the outlet. But I still have that high outlet temperature that I need to deal with. So in those particular cases, again, you see that on the site chart. So in those particular cases, then we add a post-cool coil, which then will take my 109, leaving the Desiccant rotor and drop it down to whatever the customer needs, in this case, 70-degree supply air. And again, that after cool flow would be chilled water or DX. Let me see that on the site. So one of the critical things with sizing humidifiers is doing the moisture calculation. So spend a few minutes going over some moisture calculations. Basically, one, you want to identify the required level. You know, do you need to maintain a space for 45%, 10% RH? What's your space? Control point, same with temperature. You want to identify your sources of load for the moisture. We'll go over a lot of the common load sources here in a few minutes. You want to add your total load and then determine the equipment required. So again, when you're determining, you know, how dry you want to dry, you know, we build units down to, you know, controlled space minus 50, 60 dew point, delivered air minus 80 to minus 96 dew point. So we can provide a lot of dry air. If you need 20% RH, you don't need me to deliver air at minus 40 dew point to your space. So again, it's understanding the loads and understanding you don't want to over dry because you pay for it. The bigger the equipment, the higher the cost and the more energy.
Walter, what kind of I mean, just for some of the people maybe that haven't been in some of the industrial spaces that we see this stuff in. You know, you'll see the really drastic areas where you need to remove basically all the moisture from the space, and then you get to different things like what industries are you guys serving in those?
That's actually coming up here. I'm going to cover that in good detail. Hang on, probably about 4 or 5 slides. And also understanding when the problem occurs. You know, a lot of humidity problems go away in the winter, the fall, winter. And we see that a lot. So understanding, you know, with the customer, when they have the humidity problem, and when they don't have the humidity problem, also helps kind of tell us where we need to be as far as design conditions. Again, understanding, you know, where you want to be, how dry you want to be. You know, if you've got outside air, you know, you need to be 55% RH, 2% RH. Again, larger the difference, larger the load, larger the cost, more energy. So the different areas of infiltration and areas you pick up moisture, combustion air, forklifts, radiator tube, gas heaters in the space, people in the space. Not only the people in a space, but what they're doing in the space. Are they exercising? Are they at rest, sitting still, working? Makeup air is a source of moisture. Wet surfaces, this would be an open tank. Typically you see them like water treatment facilities. Permeation, this is you know, wall construction. Is there any vapor barriers, anything to prevent the permeation through the walls? Door openings is an area of moisture infiltration, and then product. The product could be several different areas of load. You could have a conveyor that's going through the space, bringing product into the space. That opening for the conveyor is going to have moisture infiltration. And if you're drying the product in the space, you're going to have the moisture you're removing from the product, dry the product that's added to the space as well. And sometimes you also have process. If a customer's doing a wash down cycle, you know, washing down a pharmaceutical or something, and they need to dry that space out to start another production run, you also have wash down to deal with. All these calculations, I'm not going to go into details on the calculations. These are all in our application engineering handbook, which is online. If you send us an email, we'll be happy to send you all these calculations. But this is the calculation for the moisture migration for permeation through the walls, floors, ceilings.
It seems like everybody wants to skip that stuff.
It's a critical step in the process. These are several factors that's used, based on type of construction, whether it's masonry, sheet metal, modular panels like a walk-in cooler type freezer panel, and then different types of vapor barriers, And this is just an example. This is all found in our application engineering handbook. It walks through examples of how to do these calculations as well. And we're happy to do these calculations for anybody as well. We talked about people, so at different dry bulb temperatures, and again we talked about at rest, light duty, or heavy physical activity. You're adding a certain amount of moisture, and we'll talk about this a little bit later. But when we get into lower dew point applications, people become one of the bigger loads. Whole process. Again, we talked about product. So if you're doing like meat drying, sausage drying, those types of applications, poultry, where your product's coming in at a certain weight, you need to dry it down to a certain weight. That product, that amount of moisture that's being dried from that product is a load that needs to be accounted for. And basically we're looking for, what's the weight of the product coming in, what's the weight of it when it's dry and you can use it. And then how many pounds of product do you want to do in an hour period? And that's how we calculate that load. Wet surfaces, again, these are more found in water treatment plants, but they're basically open tanks of some kind of a fluid that would add moisture. Some of the critical things to deal with when you're looking at wet surfaces, number one is how the air is hitting that tank. Is the air perpendicular to the tank? Is it parallel to the tank? That's going to affect how much moisture is picked up. Also, the temperature of the fluid that's in the tank and the velocity that the air is hitting the tank. Gas burners, again, direct fire flame in a room is going to add moisture. Whether it's natural gas, propane, typically they're from like forklifts, again, indirect or direct fire gas heaters in the space. Fixed openings, you see a couple examples of a room. You got pipe penetration, conduit penetrations, any type of penetration going through that room. And as we talked about conveyors, and you can kind of see here the less humid space, you can kind of see just the normal infiltration of the more humid space infiltrating into the less humid space in both examples. Here you got somehow ways we deal with those to kind of reduce that amount of moisture. One is pressurization. Get some high velocity airstream through that opening whenever you can. Kind of difficult on conveyors because when you deal with the conveyor, you got to look at product weight and everything. You don't want to just shove 1,000 feet per minute of air through an opening and they blow the product off the conveyor. So you got to pay attention to that. Another thing that we do is basically build like a tunnel around that opening. The longer the tunnel, the less moisture that infiltrates. So, typically tunnels for conveyors, we typically do about 2 or 3 foot into the more humid space. Again, here's a calculation for that infiltration. Door openings, again, how many times people come in and out of doors per hour affects the moisture. You can see, moisture is going to spike whenever you have a door opening, so you got to account for it in your calculations. Typically what we do for sizing purpose, if we don't know if you got 10 people in a space, we're going to assume about 10 door openings per hour, unless someone tells us different. Again, the drier you want to go with the room condition, the more you want to control in and out of people into that space.
Walter, how many grains of moisture in a pound?
Yes. I don't remember that number.
I just for a relative, 7,000.
Yeah.
Okay.
Earlier slide.
Yeah, okay. I'm just trying to relate, like, you know, we talk about pounds per hour and humidification all the time. Like, what is that moisture? Everything here is in grains, and I just wanted to.
So one of the ways we combat door openings per hour in a more critical space that needs to be held at a critical condition at a lower dew point or RH is we build in what we call an airlock, which is basically a small room vestibule, so to speak, that has two doors. And typically those doors are interlocked. So someone will open the outside door from the more humid space, that door will close, it senses the door is closed. And they gotta, and a lot of times they gotta be in that interlock, that airlock for a certain period of time, typically about a minute, before that second door allows them to open. Now, there's emergency things, so if you got an emergency exit, you can exit and bypass the timers, but that is a way to combat the infiltration of door openings per hour.
But according to this, the airlock is in the condition, part of the conditioned space.
The airlock can be in the conditioned space or outside. We do.
You're just holding a transition zone.
Yeah.
Okay.
And we've done where they're kind of half in, half out. Well.
I'm really glad you're covering all this stuff because it's important. It's important.
Makeup there is one of the things that typically gets forgotten during dehumidification, that when we're doing our sizing, you know, someone just says, we need you to control the humidity in the space. We'll do the temperature control. But one of the things that they forget about is if they're bringing fresh air into their air handling unit for temperature control, that's adding moisture to my space. If they're doing all return air, that's different. But if they're bringing outside air in, fresh air through the air handling unit, I got to know that so I can add that load. That's a load that's added to the space that I need to handle on my dehumidification side. So typically, you know, we do fresh air a couple different ways. One, we bring it right into the dehumidifier through the makeup air. Or it's brought in through, again, the other source, but we have to have the CFM to overcome that additional load. Again, applications manuals available online.
It looks like you got some questions popping in.
That's, that's from a while ago.
I'll get those notes out.
So kind of go over controls of our systems. We do two different types of controls. Back 2001 and earlier, they were all relay-based controls. After that time, we started migrating over to PLC control-based. Now everything's PLC control-based, unless you want relay logic. We do have some customers that have, you know, maintenance men that have been with their companies for 50, 60 years, and that's what they want. They want the old relay logic. So we still build a few of them a year. But if you buy just a standard unit, you're going to get a PLC based unit. We control the reactivation heat source. Again, heat sources can be many different sources. We'll kind of go over how we control each different type. We control the moisture level, and that's with dehumidification. We also add humidification. If it's a very critical environment, that's, you know, they got to be 35% RH plus or minus 1% RH, and bringing all outside air in the winter, you may have to add moisture.
How do you
So we
control,
do package with humidification as well.
how do you control dehumidification? Do you modulate the burner, modulate the wheel speed?
I got a slide here.
Oh,
Shortly after that. Yep. Then we control temperature. Again, talking temperature. The temperature could be, you know, the pre-cooling, the post-cooling, or the heating could be preheating. You know, again, for bringing all outside air, you may have to heat the air. Or it could be towards heating as well. Again, the modern controls, PLC, we have a HMI on the screen. We do have building automation communication as well, tie into building automation systems. And it's just typical kind of control layout. We have a PLC or HMI. We have a switch inside the unit. On the outside, we have a laptop port with a receptacle, so an RJ45, so that you can plug your laptop in without opening the control box. And then again, we have the backnet module as well. Now we start talking control of humidity. So basically, modulating the reactivation heat source is typical how we would do it. You get plus or minus about 3% RH if we do that. If you want tight control, we do phase and bypass around the Desiccant rotor. We don't really modulate the speed for humidity control of the Desiccant rotor. So we either modulate the reactive heat source or the phase and bypass dampers around the Desiccant rotor. Is how we'll control that. Again, tight humidity requires tight temperature control. I mean, I've been on the jobs and where especially someone else was doing the temperature control, we were doing RH control, and you know, if they're not if the temperature is fluctuating or humidity, and then it's a back and forth kind of whose units were not performing. So chilled water. So now we're going to talk about how we control cooling. Chilled water. Our glycol systems, we use a three-way mixing valve. What we typically do is we provide that mixing valve already, unless the customer wants to provide it themselves. Refrigeration. For coarse control, we use compressor staging. And then fine control, we'll either use a phase and bypass around the coil, or we'll use electronic expansion valves. For heating, again, we use a three-way valve for heating. Gas, we modulate the gas valve, modulating gas valve. Steam, we do phase and bypass, or we use a steam valve modulation. Any questions before I get into applications?
I just have one, and it's sort of a general one. So it's, you know, for a long time, I can honestly say I didn't understand a lot about dehumidification using the solid wheel. And now that, you know, I've sat through a number of presentations, it seems like there's the controlling the wheel itself to get rid of moisture is a fairly simple and predictable process. And that the difference between manufacturers of Desiccant systems, it's really on the application know-how side. Like, is that a fair?
Yeah, I mean, the application, the know-how.
Like maybe your wheel's a little deeper, but
So remember, there's in the industry, there's really two depths of rotors.
right,
There's a 200 millimeter and then a 400 millimeter depth. Those are about the only two industry depths. As far as diameters, because diameters also kind of affect performance a little bit. There's pretty much an industry standard on the diameters.
Yeah.
Where it really comes into play is, you know, really optimization of the design.
Right.
And that's, you know, we talked about rotor speed, those kind of things. That's things that our applications engineers look at when they're determining the best cost-effective solution for your need to meet the solution. We'll look at a 200 millimeter versus a 400 millimeter. We'll look at rotor speeds. How fast I turn that Desiccant rotor affects how much moisture I remove. How much reactivation heat. Again, if I can get by with using 200 degrees reactivation heat instead of our normal 285, I would be colder on our process outlet side. So, you know, we look at, you know, is it a critical temperature control? Do I want to keep the cost down on the cooling, post-cooling side? If it's, you know, lower moisture removal, you know, we're talking, you know, 35% RH, 30% RH. I may choose to lower the reactivation heat source temperature to get colder air come off to the process side of the unit.
And then is there an agency that, like with air conditioning, there's certified tests and all that kind of stuff? I don't imagine that there is for Desiccant dehumidification.
There's not nothing. I mean, ASHRAE has a Desiccant dehumidification kind of committee.
But there's no like certification.
They haven't put any standard out.
Right.
For that.
Okay.
So, you know, each rotor manufacturer kind of has their own laboratories and does their own, publish their own testing.
Right. So it kind of boils down to, can the manufacturer handle the application and do you trust them?
Yeah.
Is what it turns into, right? Okay.
Applications, condensation, frost prevention, corrosion prevention, moisture regain, mold, fungus, product drying, preservation, archive, and controlled space for manufacturing processes. And we'll go through each one a little more in depth. So, mold, fungus, and I would look at surgical suites, because we've seen the increase in operating room surgical suites, from the dehumidification side. It's becoming, more of a common, market for us over the last probably 6 or 7 years. Again, in most applications, we need to know the city, the state, units indoor, outdoor. If it's an outdoor unit, whether it's on the grade, whether it's on the roof. You typically need to know size of the room. And I've seen this a lot, so we deal with cubic feet, volume of the room. A lot of people just say, "Hey, I got 5,000 square feet, can you humidify it?" Well, if I got an 8-foot height versus a 20-foot height, it's 2 different things. So we need to know the volume of the room, the design conditions, tolerances, surrounding conditions. If I'm dehumidifying this room, what's surrounding each wall. Is it outside air? Is it conditioned air? The construction of the room, people, door openings, makeup air, cooling on a typical surgical suite, especially a hospital. They probably already got chilled water plant, hot water, so you simply want to use that. Sometimes we may need DX. Filtration required, external static pressure, if there's an existing air handler. So typically we see about 500 CFM of outside air per surgery room. Typically you see temperatures around at 50% RH, about 55 to 68 degrees. I've seen from experience, we had one operating room that it was, we were going 40% to about 60% RH, and it really depended on the surgeon more than the operation or anything. We'd have one surgeon with one condition, another surgeon with another condition. So I found out that's a very
Isn't it funny how the
customer.
surgeons are in charge, but shouldn't it be like what's best for the patient who's got?
Yeah, shouldn't there be a defined standard?
I'd like it a little drier.
The surgeon's comfortable,
Yeah.
it's probably good for you, right?
But I mean, they do drive it. They do drive it.
To the best spot.
Typically we see about 2,000 CFM per surgery room, 25% outside air.
Is this a big part of your industry doing?
I would say this is probably about 5% of our.
So you do
I mean, it's not an
100 surgery units a year? Would that be something to say?
I mean, we don't do that many, but.
Okay.
Probably nationwide, I would say it's probably.
Sure. Yeah, the trouble is where you're gonna put the dehumidifier, because you gotta get your supplier, your outside air in and out, and
Existing hospitals, I mean.
they're
The
loud.
cavity, the plenum space, the
Yeah, it's tough.
ductwork and all that above the drop ceiling is very limited, so it does become a challenge, these types of projects. Typically, we see internal liners on the unit, a double wall internal liner. That liner could be aluminum, stainless steel, wipe down, wash down, UV lights on coils, filters, something added on. High levels of filtration, typically got mermaid pre-filters with a higher final filter, and then typically got HEPA outlet filters on these units as well. Pretty common feature.
Is there a purge segment or something for cross contamination between the air streams on your wheel?
No, we don't have, not on these applications. We haven't run in where we need. We really don't see much cross contamination, so to speak, on the desk road. Pharmaceutical, nutraceutical, these are very similar as far as the types of data you need. The only thing that may be different is if you're drying a product, you may need to know the product moisture. Tabling manufacturing process. Typically see these rooms about 25 to 30 air changes per hour. Space generally has a high sensible heat load, low latent. Typically see these about 70 to 75 degree Fahrenheit, 25% RH or less. And typically these are 100% outside air. And it's a dusty environment, so filtration's very critical as well.
So you filtering the return air then before it gets.
Hard shells, typically those are about 30 air changes an hour. Pressurization, these rooms are typically negative to a hallway. Simply we see about 68 degrees, 40% RH in those room conditions. Again, they're concerned about mixing air, so how we do the ductwork, everything's very critical. Low conditions are somewhat hard to do on this, but typically we see about 8 degree F and about 5 grain delta. So if we want to control the room at, let's just say 35 grain, we need to deliver about 30 grain to that room. Again, same kind of requirements, wash down, UV lights, high filtration. Archival storage, this is, fine arts, photos, film, paintings. We've even seen this in the medical, where, there's certain medical, we have one application that's actually a human brain that's being stored in a room that has to have a certain maintained in it. So quite a range of applications for this. Same kind of requirement. The only thing here that sometimes is added, and it's really not on the slide, sometimes you may need like carbon filtration on the type of media you're storing in the environment. Typically we see about 35 to 75 degree and 30 to 45% RH. Again, it's really just dependent on the type of item you're storing. Food processing, meat, poultry, cheese, frozen fruits, freezers, loading docks. Also, candy manufacturing, gummy markets now kind of a new market that's cropping up where they're producing gummies. Again, same type of requirement. This one here is again got product load because typically you're drying a product, so you need to account for that product load.
Hey, Walter, what's driving is the wheel size driven by the dehumidification or the airflow required?
So we try to design the wheel based on the dehumidification requirement. So we'll do a lot of applications that requires more cooling, and we have face and bypass humidity control, but we'll do a constant bypass of a certain amount of air if we need more airflow for temperature control.
Okay,
We'll
makes sense.
bypass
That
the
makes
rotor.
sense.
Keep the rotor again as small as possible. The smaller the rotor, the smaller the reactivation, the lower the energy. So that's something our applications engineers look at is, what do I need to dehumidify, what do I need to cool, and do it with the most practical system. And in this case, it's a constant bypass. So either we'll bring the air all into one common return, bypass a certain portion, or in some cases, we have two separate returns.
Right.
We have part of the return and mixed with the outside air. Then after the rotor, we'll have another return.
So the only reason why you'd bypass is really to allow provision for pre or post cool.
Yeah.
Okay, that makes sense.
If the air is coming back pretty warm, we may want to pre-cool it with the outside air.
Got it. Thank you.
So for moisture regain, you got conveying, storing, mixing of dry ingredients. This could be flour, sugar, starch, spices. Again, same types of requirements. One thing is we need to know what you're conveying. If it's flour, if it's sugar, because there's certain temperatures, certain humidities that certain products do better at. Typically, you'll see similar requirements in food and pharmaceutical. Outdoor air pretreatment. So we'll treat outside air. On an operating room, we've done they're close to being able to maintain the conditions. they just got so much outside air, they just need us to knock the outside air. So we'll put a dehumidifier before their air handling unit, just treat the outside air. Then our supplier will feed the outside air opening of the air handling unit. Pneumatic conveying, again, this is conveying materials, typically sugar, flour, salts. This here is typically, they got high pressure blowers for conveyance. We need to know the ICFM of those blowers because of the higher pressures. Again, we have a chart here that kind of tells, you know, the different temperatures, dew points, RH for different various items we see during conveying. Water treatment facilities, typically we see these about 35 to 40% RH. The dew point, they try to maintain a dew point below the lowest coldest temperature of the coldest surface. So we use what we call condensate control. So we'll send with the unit a pipe sensor that is mounted on kind of the coldest pipe in that water treatment plant. So we're getting that pipe temperature, sending back to our control unit along with the dew point of the space, temperature of the space. And then we maintain and control the unit based on that pipe surface temperature.
You ever seen?
No, we see, like we mentioned before, Quest is always kind of like the dehumidifier I've seen on wastewater. Have you seen anything different? Yeah.
We do about, I'd say probably about 4 units a year. I mean, it's not a big market.
Mostly down south?
No, we've done several in the Ohio area. And a few of them, well, Chicago, we did a big one a couple years ago. Again, same kind of temperature, same kind of data, but here we need to know temperature, the water at various seasons. And again, open tanks come critical in water treatment. Silos.
When you're doing a wastewater plant like that, is there a balance between pulling moisture off of the surface and, I mean, how do you balance that? Because I imagine you bring that dew point down, depending on the temperature.
So we bring the dew point down, you know, again to just, I think it's 5 degrees below that pipe sensor. So again, it's as the water changes, the outside air changes, that setting is constantly changing. As that pipe temperature changes, our dew point changes. The set point automatically. Again, silos, storage bins, this is more for product storage. Again, flours, silos, sugar silos, those kind of things. Some of the problems that people encounter with silos, if they don't dehumidify them, you know, the product will kind of what they call a rat hole, product to build up along the sides of the silo. You could have a bridging effect. Or you could have just blockage in general. So
Can you need to
that's
sell them
why-
inside your dust collectors?
Right?
That's what happens.
So typically, this is, you talked about our manufactured product line. This is a good application for a manufactured product, or a compact product. Because they're small, they can typically mount. A lot of people build a little platform on top of the silo and mount the unit right on top of the silo.
It's a fine line between creating a very explosive dust and
Right.
and having these things clumped together.
Everything drops right into the hopper, but it blows up sometimes.
And probably the newest market that has really kind of picked up the last 2 years especially is lithium battery manufacturing for the automotive electric vehicles. I have to say our business doubled last year just because of this market predominantly. It's been a big market. Basically, what you see in the facilities where they manufacture these lithium batteries for automotive, they need to be at a -40 dew point typically in that space. So you got to have dehumidification to get. It's very critical dehumidification to get to that low dew point because any moisture in those rooms will cause problems with the manufacturing process of the batteries. So a little different requirements. Actually, they're not as extensive of requirements to figure out The size of equipment. From an application engineering standpoint, I could do probably 10 of these projects as fast as I could do one regular project because the data is so minimal what we need. You're basically looking at the volume of the room, number of people, the door openings per hour, exhaust CFM, heat loads for customer equipment, the surrounding space. That's it. You're not looking, you don't have re-infiltration because these rooms have got to be sealed. From supply ductwork, return ductwork, all the way to the rooms. These are zero leakage type rooms. So they're sealed, so you don't deal with infiltration. There's typically no conveyors going in and outside these rooms. Everything's brought into airlocks, even the material. They build bigger airlocks for like forklifts to drive into, lower, 2 or 3 pallets. The high-speed roll-up door shuts down. The material stays in there 5 to 10 minutes before someone on the inside will open the inside roll-up door and then pull that material back into the space. So all entrances is through airlocks that are all timed so that you can't open the inside outside doors at the same time.
Walter, you speak about the envelope and all of the infiltration and permeation. One of the big frustrations I've had with my customers when they are looking at applications where they do this is that, the customer, the end user looks at it as like, okay, this isn't just a piece of equipment that's going to do, they have to make a significant investment in shoring up the infiltration that's coming into that room. How critical is that for your guys' design process?
I mean, it's very critical because, we design based on what we know and what we do. So we've had cases, I can think of so one of the markets that we don't really sell a lot into is the tire manufacturing process, what they call the grill rooms, where all the rolls of the steel braided wire go into the tire. So all that is in a controlled room. And we had one case where, we got the survey sheet, built the units, went out because they were having problems maintaining the space. And we went out, so all these wires feed through openings in the wall. And instead of the wires feeding through a little small opening, they just cut a big, like 4 foot by 4 foot opening. And then they had a bunch of wires going through. We didn't know anything about that. So again, what we know is what we size equipment on. So to prevent any kind of last minute, the unit's not working, what do we got to do? Well, you got to put a vapor barrier up. It's good to try to, make a site visit, get photos if you can of, pipe penetrations, conduit penetrations. If you see openings, take measurements, because we can design a unit to probably handle it if we know, this space is not sealed up at all. Vapor barrier, we can design a unit for that. Versus, this is a tightly constructed room. Again, you're going to pay more for the equipment because you got to oversize it to make up for those openings, those kind of things. So again, lithium batteries, and this kind of goes into any kind of brewer application. Incorrect data will ensure trouble meeting space conditions. So we just talked about that. Again, when you're talking a -40 dew point, any door opening should be at a minimum. Really try to educate customers. We got 10 people in a space. They're going opening the doors 20 times an hour. You're going to pay dearly. I mean, your dehumidification costs are going to be double what it would be if you kind of control that 10 openings per hour. So really kind of control that. Typically, these units have purge to get down to that. We got delivery area in that -80, -90 dew point. So we use a purge. So all the air comes in through the outside air through a common outside air opening. That air then gets pre-cooled, mixes with return air, which gets cooled again. And then we pull off some of that air through what we call purge, which is another sector in the Desiccant rotor. It goes through that sector and then feeds into the reactivation. So the reactivation air is dry, going into the rotor, just like the process air. And that's what allows us to achieve that -80 dew point that we need. Oh, one other thing here. So one of the things we do in these, and Tom, we could talk about in other applications, is typically these types of rooms require a lot more sensible cooling or air changes per hour. You need cleanliness ratings, ISO cleanliness 10,000, those types of ratings. So, we're talking 60 air changes an hour. In a lot of cases, you don't need that much humidification. So one of the things we do on these markets is we use HEPA hub fans in the room, in the plenum, to circulate the air changes per hour as required. And to do additional cooling. So we'll incorporate sensible cooling on those HEPA hubs to handle that additional cooling. Just to cut down on the humidification.
Right.
Size and cost. Again, how critical these dry rooms are is we partner with a dry room manufacturer. So we offer a complete kit, which is the Desiccant dehumidification and the room. Because one of the things we saw early on in this industry is there's a blame game. So especially with the automotive, when you have carb failures, carb fires, those kind of things, and recalls, it's the room manufacturer, it's the dehumidification manufacturer. That's why we didn't maintain, and that's why this product is scrapped, or we got to do all these recalls. We found early on it's better to go in with a common approach, common design of a room and a dehumidification unit. So we partner with someone that makes these rooms. We've done several projects. We know from the dehumidification side, we know that room construction in and out, and they know our equipment. So it's kind of a packaged, pre-engineered package design.
What kind of panels are you using?
So they use an IMP type panel, 4-inch thick. Again, sealed inside, outside.
Oh, Kingspan, right?
I think that's one of the manufacturers. There's a lot of manufacturers that make them. Again, you can see these rooms are done. They have windows in them. They can have glass walls. So this whole wall is a glass wall. Again, when you're talking a low dew point, you want to keep people in the room at a minimum. So one of the things we found is there's a lot of R&D facilities that start up. People with this market, people want to get to the market. So they're all coming up with these ideas of, I got the best lithium battery, whether it's going to be reduced energy, make my vehicle go longer on a charge, whatever it is. There's a lot of these mom and pop R&D startup companies popping up. They want to do these small R&D labs, about 1,000 to 1,500 square feet. And one of the first things we saw is, well, we're going to have 10 people in the space. Why? Well, we got investors that's coming through. Well, how many investors? Well, 5. Well, let's put a glass wall down your room. They can see inside what's going on, but they don't have to add load to my space. So we've done that.
Walter, can you check the question up there? My computer just died. Package solutions for archive spaces.
We don't have packaged solutions, but we can. Now that we just started this approach with the lithium battery manufacturing. So if there's other markets out there where people want a clean room, a dry room, on whether it's some kind of material drying, we now have a product that we're comfortable with. And we can, whether it's archival, any kind of manufacturing candy foods, we can go to market with this kind of same concept.
But do your kits include airlocks, or do you?
Yes, it's all included.
Okay.
Again, it's basically a kit that we ship the materials. We have installation crews throughout the US that have installed these rooms. Or we've had, people at a facility installing them. I'm gonna send a supervisor out to just supervise, because we want to make sure it's done right. So we'll send a supervisor out for 2-3 weeks to assemble a room, typically a 1,000 square foot room, typically can be assembled in about 3 weeks. And we educate them, okay, you gotta make sure you seal here, here. So we educate them. Typically in these units, because air leakage is a problem with ductwork, we provide the supply air and return air ductwork for the room. Typically what we'll do is we'll install the dehumidifier as close to the room as possible. And what we've come up with the design is, and we'll see here in a few minutes, is it's basically a structural steel platform that goes above the room. The dehumidifier sets on top when you have the ceiling height. It'll set on top, and then it's just short ductwork runs with completely sealed ductwork. If you don't have ceiling height, we try to put the unit indoors next to the room. We've done them outdoors. Again, leakage is an enemy in these types of environments. One pinhole leak in a minus 40 dew point space, you're gonna be chasing that problem. So yeah, we do duct work, we do, the HEPA recirculation, air changes an hour. So here's kind of the structural platform. So right now there's no room. So basically you install a structural platform, you set the DHU on top, and then you construct a room. That also allows us, this structural steel carries the room, ceiling, the wall load. So there's no load on your existing beams in your building. And there you can kind of see, so there's a plenum cap, and there's what we call an IntelliGrid ceiling, drop ceiling. There's about a 3-foot cavity that we do. We bring all the return supply air in, and then we distribute the air through the HEPA hubs as required. And there's another look. There's one of the inside of the room. You see the ceiling, the drop ceiling grid. This here, not only we do our duct work, but a lot of customers want this nice clean room. So, any of the NEPs for communication, electrical, all those can be ran into this plenum. That way you got a nice clean look.
Where's your return air?
So the return air is a low wall return air. So we actually build chases in the room, cavities with the same construction as the walls that are the low wall returns. Again, doors, we have swing doors, double doors, sliding doors, high-speed roll-up doors. Again, we, as a single source, this is where we went to the market. When you have a problem, if you do have a problem, which we haven't experienced any, if you do have a problem afterwards, you come to us. You're not gonna, okay, was it the DHU manufacturer, was the room, you come to us right here. And there's one of our typical dry room units. A factory.
What's the lead time for one of your?
So right now we're about 20 to 26 weeks lead time. And a lot of that is more parts driven than manufacturing availability. We for like fans and stuff, we're seeing like a 12-week lead time for our fans and coils and some of our internal components.
What CFM range are you?
We do anywhere from 100 CFM all the way up to about 55,000. We're actually building one right now on the plant that takes about 48,000.
Wow.
CFM.
When you're doing your, what was that?
I didn't know what the load number was in there, 100?
100
100 was
CFM,
the load.
yeah, we have our, what we call our compact mini pack product line. That starts out at 100 CFM and goes up to 1,800 CFM. There's soon be a 2,700 CFM compact unit. Those are typically in stock, ready to ship. So if you just buy it off the shelf, typically it can ship out same day in a lot of cases.
Those are all electric regen.
They're electric reactivation. Again, we package them if you need them packaged, but there's no cooling options with those. They're just a standard relay, kind of low cost, small unit.
So when you do it,
Side stream it with
You can side stream it with a makeup air unit. Yes.
a rooftop unit.
when you're doing your pre and post cool and it's DX, like that's a little bit of a hairy combination sometimes because you're No, I mean,
So we use two separate condensing units. So if you got DX, we have
right,
pretty cool to separate DX and a post cool to separate DX.
it's because the airflow is so low and
Yeah, when we use hot gas bypass, electronic expansion valves, liquid inject, all to keep the condensing units out.
other questions, guys?
So you could take a package unit for a surgical unit,
Yes.
put an outdoor surgical unit. Because hospitals don't have much indoor.
Yeah, we do indoor, outdoor, any kind of specialization. I mean, like this is our standard unit color, which is beige. We do gray, we do whatever color you want the unit painted. We've even done two-tone paint jobs where, and outside of a building, our unit was about 8 foot tall. There was a paint line on the outside, stripe basically on the outside of the building and 3-color scheme. We matched that exact, so looking at it from the road, it couldn't see the unit stand out.
You've got one in the chat, Walter. Or I'm sorry, the Q&A. Oh, we already answered that. My bad.
Answer is yes.
With regards to, we use an Allen Bradley micrologic PLC, but we're custom shop. So if you want a Siemens PLC, we'll sell you a Siemens PLC. We use a New York blower, but if you want a green head fan, we use green head. You name it, we can accommodate. Same with VFDs. We have Allen Bradley VFDs, one at Schneider and Scala. You can accommodate all those types of things.
Great. Sounds good. How about a nice hand for Walter and BryAir? Well, setting up lunch, just wanted to thank everybody for coming. Thank everybody who was remote. Appreciate your time. And actually next month, I'm the speaker. I'm going to be talking about, this is sort of Tom's take on decarbonization. So we'll be talking about CHP, gas-fired heat pumps, air source heat pumps, and just general information about decarbonization now. So look forward to seeing you all next month. And if you can tolerate me for a couple hours, that's what you're going to get. I'm working on a special guest. I'll keep you all posted. All right. And that's a wrap, Steve. Thank you all.